Hello, everybody. We'll give it maybe a minute or so here just to give a chance for everybody to log in and get started. Um, okay, I think we've given a little bit of time for everyone to get into the meeting and get comfortable. Welcome to the Acoustics Technical Working Group today and tomorrow, hosted by the NASA Glenn Research Center out of Cleveland, Ohio. My name is John Lucero. I am the branch chief of the acoustics branch at Cleveland, Ohio, NASA Glenn. On Thursday, we also have the Urban Air Mobility Noise Working Group, so I'm hoping you can attend that as well. I'd like to take this time to thank NASA management and the projects that are funding this meeting. And also, I'd like to thank all the speakers today, especially the invited speakers from the FAA, Levant Aleri, Arthur Orton, and Mooney Majiji. Also, I'd like to thank Lawrence Vogt and Matthias Eim. Also from Penn State tomorrow morning, we have Kent Brentner. And I'd also like to thank all the volunteers who have taken their time to make this happen. Chris Miller, Jordan Klutz, the NARI team from Ames Research Center, Lina Eskridge, Jonathan Nguyen, Rajan Shankara, Kanit Mlaudzi, and also our IO operators, David Stevens and Devin Boyle from NASA Glenn, and Eric Greenwood from Penn State. And tomorrow, Rand Cabell, Steve Rizzi, and Brenda Henderson. We have 390 attendees from 24 countries this week, representing industry, academia, and government. We have 3 days of presentations, the last day ending at noon with subgroups breaking out in the afternoon. Now, I want to remind you all that these presentations are works in progress, more like teasers for you, so to speak. I encourage you to use the IO tool, which Chris Miller will explain in more detail. Please use this IO tool to reach out to the presenter with your name for more detailed questions so we can put the speaker in touch with you. At this time, I would like to introduce our Master of Ceremonies, Chris Miller, who will lead us into the presentations.
Okay, thank you, John. So as promised, I'll talk a little bit more about the Conference IO tool. It's a way to capture questions and have the audience vote up the ones that they'd most like to hear in the limited Q&A time. But we will be capturing all of those and passing them along to the presenters for the presenters to hopefully write written responses that'll be then collated, and they'll come out with the presentations about 2 weeks from now, I think. What we normally do is let all the presenters make final revisions. There's nothing like giving a presentation to identify some typos or something that you missed. So the presenters will tweak their presentations. They'll give us a handout copy. We'll combine that with the written responses to the questions, and that will all go out to the registered attendees. So thank you very much for registering. The time spent by the speakers on these great presentations, we really appreciate it, and we appreciate your interest and feedback from the audience. So I wanted to mention that we, the speakers and sort of the stage crew, we are on Teams. That is then streamed through YouTube to the audience. There's about a 7-second delay. And so if it seems like there's some awkward silences, we may be just waiting for questions to pop up in the Conference IO tool and get approved, and then we'll see them and so on. So that's the plan for the morning. If you have any questions, throw them in the IO tool. Even if it's something about, I can't get the agenda or I don't hear anything, somebody will try to help you out. And so with that, I think I've covered, covered all of my my notes here. The morning session today is going to be a higher TRL level work. NASA and academia is usually a lower technology readiness level, and the FAA, through their continuous lower energy emissions and noise projects, have been funding transition of that lower TRL level work to higher TRL levels. So this morning we have an overview of the Clean 3 project work packages. That's from Levent and Arthur. And after that, Lorenz Vogt from MIT has been working on an ascent task where he's doing optimization. And so those are tying together nicely. This afternoon, which will be hosted, or master of ceremony will be Jordan Klutz. That will be more jet noise work. So we have Brenda Henderson with an update on the Learjet. And then some work internal and under SBIRs on jet noise. If we have any questions, we have a few minutes. We normally, if this was in person, this is the point where I go through the safety briefing. If you hear a fire alarm, then bring your seat backs and tray tables to their upright and locked position and go out to the back and exit. But we don't have to do that. So we're a touch ahead of schedule, and we've had no technical difficulties. So I have a couple of minutes here, and then we'll probably transition into Levent and Arthur's talk a few minutes early. There's probably no real need to have dead air for 5 minutes. So why don't we give it a minute or two, and then we'll turn it over to you. Levent and Arthur, are you guys ready?
Yes, we are.
Yes.
Okay. So let's also do a tech check for David Stevens, who's volunteered to be the moderator of the questions. I think we heard you earlier. Is your mic and all? There you go. Okay.
Yes. Good morning.
All right. So, let's. I guess we'll just proceed, and we'll be a few minutes early. One of the nice things for the viewers on YouTube is you can pause and replay the video, so that's kind of convenient if you need to duck out, or if you are worried that you came in late, you can always rewind it and and catch up again. So, all right, with that, thank you guys, and take it away.
All right, great. Thanks so much, Chris. We are going to be presenting our Clean Phase 3 projects under this briefing. Thanks again for organizing the Acoustic Technical Working Group meeting. I know that we, as the FAA, participate in these meetings on a regular basis. And as the title of this slide says, Clean Phase 3 is a program that we have just initiated over the past few months. And this will be our first time presenting our projects on the acoustic side of it. And so with that, I just want to introduce myself. My name is Levent Ilir. I'm the FAA's Continuous Lower Energy Emissions and Noise Program Manager. And along with me is Arthur Orton. He's a Deputy Program Manager for the Clean program. So with that, we can go to slide 2, please. All right, so in this presentation, we're going to be providing two different sites. One of them is going over the Clean Phase 3 overview about what the program is and what it does, what its function is. And later, we're going to talk about the acoustic technologies specific to this meeting that we are having today. All right, next slide, please. All right, so just to give you a little background on the CLEAN program, we started the initial phase of the CLEAN program back in 2009-10 timeframe for a period of 5 years. This was a trial period, and our annual budget from the FAA side was $125 million. And the purpose of the program was to be able to create an environment where we can try to reduce fuel-borne emissions and noise via aircraft and engine technologies and alternative jet fuels. We also imposed a requirement to the companies who we select is that there has to be a public-private partnership with 100% cost sharing from the industry. So what that means is that every dollar we put in, they have to match the same amount or more to be able to continue their projects. So we established some goals related to noise, fuel burn, and NOx, which are listed on the second column under phase 1, as you can see. And with the success of the program that was finalized around 2015, we also established an entry into service that was 2018. And we had some success stories from that. And based on those proceedings and how the benefit of the program was, we initiated the second phase of the program around 2015-16 timeframe, again for a period of 5 years. We established a budget line of $100 million for the following 5 years, and we established new stringent requirements for our fuel burn, NOx, and emission goals, which are listed on this table. I'm not going to be reading those because you have this slide video. And then we, again, from the follow-on successes coming from phase 1 and phase 2, we decided to continue with the third phase of the program, which are listed on the last column. So if you go to the next slide, Arthur, I will be able to give a little bit more overview. So the purpose, again, to be able to reduce fuel burn, emissions, and noise. At the same time, to be able to mature those technologies that are at TR levels 3, 4, 5 into 6 and 7. And our purpose is to be able to expedite the technology introduction that could be enter into the current or future aircraft and engines. We also looked at an option, for example, for the alternative fuels. We had some changes in our policies, and we included a statement here. You can see it on the last bottom of the screen, saying that we are looking at advancing the development and introduction of hydrocarbon jet fuels for aviation that can enable improvements in fuel efficiency and reductions in emissions. That also includes fuel blends. The one important thing on this chart that you'll see in here is that the table is divided into two segments. One is subsonic and the other side is supersonic. For the past two CLEAN programs, phase 1 and phase 2, we did not have supersonic aircraft. And in this one, we are imposing this requirement where we are looking at reductions in noise, fuel burn, and NOx, as well as looking at PM, particulate matter goal reduction in subsonic aircraft. We also included another goal for the noise reduction for subsonic aircraft is that we are looking at reducing community noise exposure. As you can imagine, as an FAA, we are getting a lot of complaints and lots of questions about how we can reduce the noise, and we included this goal to see what we can do to mitigate the impact and the noise coming from aviation. So with that, we can go to the next slide. All right, so this slide is an overview of the entire CLEAN phase 3 technologies. So as you can see, we awarded contracts to 7 companies. We had 8 that we selected, and we're working on 1 being negotiated at this time. That's why it is not in here. We included all of our technologies on an aircraft view, where anything that you see in green color, as the footnote on the left corner says, they are related to fuel burn reduction goals. Anything that's in red addresses emission goals for the FAA. And anything that's in purple is for the noise reduction. As you can see, we have awarded contracts to General Electric, Honeywell, Pratt & Whitney, Boeing, this America's Phoenix, Collins Aerospace, and Safran. I believe I counted all the 7 ones in here. And subject names or the technology names are also attached to each line where you can see it in here. So with this, as you can see, we are targeting a number of aspects of the CLEAN program to be able to help us mitigate the environmental impact of aviation from the fuel emissions and noise aspect. So in the following slides, Arthur is going to be talking about the noise aspects related to this meeting, where he's going to be talking about all of the activities in purple color on a forward-going basis. So with that, I will give the mic to Arthur.
Great. Let me just reshare here. Thank you. Okay, thanks for the introduction there, Levent. So I'm going to be stepping through each of the CLEAN companies where their awarded technologies will be focusing on noise reduction. As you saw on the prior slide, every one of those purple technologies I'm going to be touching on here, and that noise is a pretty big portion of our technology portfolio in terms of the environmental benefit areas we're trying to target. It has consistently been one of the more challenging goal areas for CLEAN through the different phases. So CLEAN Phase 3 is putting quite a lot of emphasis on this. So what you'll see is the 6 companies working noise technologies and just those technologies pertaining to noise. I'll give you some information at the end here on how you can engage to learn more, but this will sort of be a whirlwind tour of our portfolio of noise technologies. The first company I'm going to talk about here is Boeing, who's working on 4 technologies relating to noise under CLEAN Phase 3. The first of these is called the Quiet High Lift System. So this is comprised of the development, prototyping, and flight test demonstration of really sort of 2 sub-technologies, flap edge fairings and vortex generators on the wings, targeting changes in airflow that overall would help aircraft noise. Estimated to provide about half an EPNdB noise reduction at an aircraft level. So that's our first noise technology on the wings itself. Boeing is also focusing on reducing landing gear noise under CLEAN Phase 3. What we're calling the Quiet Landing Gear project is focusing on developing noise treatment applications for landing gear doors, as well as aerodynamic shielding for the gear to reduce some of the turbulence coming off the gear and thereby reduce noise. This project is planning to prototype these items and take them to flight tests for noise measurements, targeting a similar noise reduction, about half an EPNdB at an aircraft level. Moving on to the latter half of Boeing's work, it also extends, their noise work also extends to the engine installation in a project called the Advanced Nacelle Next Generation Inlet. This is really building upon some short inlet work that Boeing conducted first under CLEAN Phase 2. And in this project, we'll be developing an engine inlet with some novel structural and systems architecture that aims to reduce weight and drag and improved acoustics relative to existing short inlet designs. So this sort of short inlet pairs really nicely with, the move towards ultra-high bypass ducted engines in the future, and we're trying to find a way to reduce noise and fuel burn simultaneously. So this is targeting up to about 1.5 EPNdB noise reduction at an aircraft level while providing about 2% fuel burn reduction. And similar to the other technologies, this will be prototyped and demonstrated in flight to validate these benefits and reduce technical risk. Finally, Boeing is also developing an aircraft technology, but not in terms of hardware, in terms of noise-optimized flight path algorithms to target simultaneous noise reduction and fuel burn reduction. So this is called the Intelligent Operations Project, and as Levent mentioned, one of our noise goals is not just to reduce the certification measured noise, but to reduce community noise, and this is doing that via operational means and technologies. So rather than any source noise reduction or attenuation mechanism on the aircraft, this is an intelligent operational solution. The concept will essentially calculate and recommend in real time optimized flight paths, which could be then requested by the pilot via future air traffic management integration mechanisms such as future data communications. New algorithms for both departure and arrival flight paths will be conceptualized and demonstrated, targeting a noise reduction of about 3 to 5 dBA peak, while saving a portion of fuel during those phases of takeoff and approach. So that wraps up Boeing's 4 technologies related to noise under Clean Phase 3. We'll move on now to GE Aviation, working some great propulsion technologies related to noise. The first of these is the open fan. So this is developing innovative open fan technology that delivers a propulsive efficiency benefit of open rotor type architectures while working to overcome some of the historical issues of complexity, weight, and flight speed limitations of those propulsion configurations. Under Clean Phase 3, GE is focused on the aerodynamics and acoustic aspects of the propulsive fan itself and the blades. GE will be bringing fan blade and vane designs into a rig test program, culminating in high-fidelity wind tunnel test validation that will take both noise and performance measurements and project those to a full-scale next-generation narrow-body application. Overall, this is targeting about 13 EPNDB cumulative margin relative to stage 5, while enabling propulsor configuration that could provide more than 10% fuel burn reduction relative to the current LEAP narrow-body engine. GE is also working on some complementary acoustics work around ducted engine designs. This is in our so-called Advanced Acoustics project, they're working on a combination of novel acoustic liners and fan noise source strength reduction via innovative designs of the fan outlet guide vanes to reduce noise in future engine architectures that are ducted. This is really building upon some prior work conducted under Clean Phase 2 with GE that did some initial prototyping of these acoustic elements. And under Clean Phase 3, GE will be taking these to subscale wind tunnel testing of the fan and outlet guide vane designs to really evaluate the noise source reduction and attenuation relative to a baseline configuration. These different features are expected to provide about 2 EPNDB cumulative reduction for the liner aspect of the project and 1 EPNDB cumulative for the fan and OGV optimization. We now move on to Honeywell, who's another one of our propulsion partners working noise reduction. Honeywell has 3 Clean Phase 3 technology projects, all of which are targeting noise reduction in one way or another via different aspects of the engine and its components, in addition to providing some fuel burn and emissions benefits against our other goal areas. The first of these is the highly efficient fan module. This is really a suite of fan technologies targeted at Honeywell's business jet size class engines. We'll leverage prior fan rig test work through collaboration with NASA to inform development of noise reducing over the rotor acoustic treatments. This project will also work on some optimization of high efficiency boosters and stators, as well as improvements to the fan exit guide vanes. In total, this fan optimization is working towards about 1.5 EPNDB noise reduction while providing 1.5% fuel burn reduction. Moving back in the engine, Honeywell also has a package of core work called the Efficient Green High Pressure Core. In the compressor, this includes sort of a co-optimization of aero efficiency and noise characteristics. The combustor design is really focusing on reducing nitrous oxide and non-volatile particulate matter emissions, addressing those goal areas, and moving back to the high pressure turbine as aero efficiency work, weight reduction work through design techniques and new materials. These will be taken through a series of tests leading up to a ground engine test in the later years of the program. So along with the significant emissions and fuel burn reduction, this core work is expected to provide about 3 EPNDB noise reduction. Finally, at the back end of the engine, Honeywell is also working on a high work, high lift, low pressure turbine targeting both fuel burn and noise reduction. Application of new advanced aerodynamic and acoustic designs is going to support these environmental objectives. This will move through, similar to these other technologies, a series of rig testing, building towards a full ground engine test in the later years of the program, aligning with some of these other Honeywell technologies. And this LPT work is expected to provide about half an EP&dB noise reduction while supporting our fuel burn goals as well. So Honeywell has kind of a nice front to back package of engine improvements, all of which have some positive impact on noise reduction. Now moving to Pratt & Whitney. Both of Pratt & Whitney's Clean Phase 3 development efforts include work in the area of noise reduction. The first of these is another fan project called the Ultra Quiet Reduced Loss Fan Stage. So you'll notice some similarities in the area of work to the other propulsion partners. This is our third and final fan noise technology project. Overall, with the goal of reducing noise and providing efficiency benefits at the same time. The technologies in this package focus on reducing aerodynamic losses and while reducing noise through some new acoustic liners as well as optimized fan exit guide vanes. These will step through a series of rig tests leading up to an engine test in the later years of the program. Secondly, Pratt & Whitney is also working on an advanced combustor, the Talon X Plus. New aerodynamic swirler designs and cooling design alternatives will be employed to simultaneously reduce emissions as well as reduction of combustor noise. Another element here is they're aiming for improved pattern factor in the temperature profile exiting the combustor, providing benefits to the high pressure turbine, which can yield fuel burn benefits once the system is optimized. So these technologies are planned to work through rig and engine tests throughout the years of the program. And together, between the fan work and the combustor work here, the total noise reduction benefit targeted is about 3 EP/dB. So now we'll move to some of the engine installation work being conducted by Rohr or Collins Aerospace. At the back end of the engine, Collins is working on large cell exhaust acoustic technology. You can see illustrated on there, which is really optimizing a cavity as part of the exhaust center body area, aiming to reduce combustion noise with application to future and as well as current commercial aircraft. You know, as other aspects of noise have reduced, combustor noise has become relatively more prominent than it was. So this is going to be targeting some optimization to address that. Collins is going to be working towards ground engine test TRL6 by 2025 in collaboration with Pratt & Whitney under Clean 3, targeting about 0.9 to 1.5 EP/dB overall noise reduction at a system level. And last but not least, Safran Nacelles is working on an engine inlet technology under Clean Phase 3 called the acoustic air inlet lip skin. This technology is really working to expand the acoustic treatment area on the inlet lip of the nacelle, but doing so by and enabled by design alternatives to anti-ice system concepts that are present in the inlet. So by redesigning some of the anti-ice, there's an opportunity to expand some of the acoustic treatment there. This has the potential to either offer lower noise for an inlet length similar to a baseline or to maintain the same noise while shortening the inlet. So the final noise benefit will really be determined throughout the course of the project depending upon its application, but really we're trying to mature the underlying technology here to open up this design space, and we'll communicate more of the benefits there as that project progresses. So in summary, this is sort of a whirlwind tour of 6 of the 7 Clean Phase 3 agreements and the technologies that relate to noise reduction. Throughout the Clean program, noise has been a very important goal for us, and you can see a lot of emphasis on that under Clean Phase 3. We found some really good opportunities to work on technologies that provide noise benefits at the same time as providing fuel burn and emissions benefits, which really helps support some of the business case for these technologies to transition successfully into the fleet in the future. As Levent mentioned, overall, we've awarded 7 agreements, and we have 1 more under negotiation. So there's a lot of good work to come here over the next 5 years, and we're excited to start telling you all about what that is. If you are interested in learning more, we conduct twice annually clean consortium meetings where the companies come together to communicate progress on their work. Our next consortium meeting is November 1st through 5th, virtually, in just a few weeks here. So if you're interested in learning more about any of these projects, we will be holding a public industry day on November 3rd, as well as individual sessions between U.S. government participants and each company on November 1st, 2nd, 4th, and 5th. So if you have any interest in going deeper on these technologies or hearing the companies speak about them themselves, you can email clean@faa.gov or cleen@faa.gov, or visit our website for more information on the project and how to contact us. And with that, I think we are complete. Thank you for your attention and interest.
All right, thanks, Arthur and Levent. So if you've participated in this virtual meeting before, you know that there may be a little bit of time required for folks to type questions after the presenters have finished, and then for the IO tool to be updated and for me to read the questions. So if you have any questions throughout the day, just go ahead and put them in. And I mean, if they answer that question explicitly, we'll just skip it, or maybe someone else had that same question. So I do have a couple questions here I could start with. The one that's been up the longest is, what is the FAA's plan regarding community engagement to reduce noise and carbon complaints?
Well, do you want to take that one, or shall I?
Yeah, just why don't you go ahead, Arthur?
Okay. So as part of the Office of Environment and Energy's efforts, you know, the CLEAN program is sort of part of the long-term mitigation path, right? We take technology development to reduce noise and see that transition into the fleet. But there's certainly a large portion of our effort within our office, especially in the policy domain and the elements working around the operational side, that do conduct concerted community engagement, particularly around, you know, at a community level, noise is a local issue. So there's a lot of effort there to engage with the community, especially as new operational changes are rolled out. So Levent and I are not directly involved in that ourselves. We're part of the technology solution side of that, but we do crosstalk and try to bring information like this to community forums where appropriate.
Okay, thanks. Thanks, Arthur. Are any of the CLEAN 3 awarded technology programs directed at supersonic applications?
So this one's a good one. As Levent mentioned, we did, for CLEAN Phase 3, expand into goal areas for supersonics, including LTO noise reduction. And if you notice, none of the technologies listed there currently awarded are focused on supersonics as a first application. However, a lot of those technologies have transferability, especially in the propulsion system, to future supersonic engines to reduce noise as well. So as part of our efforts, we're going to be looking at which technologies have that dual application path and trying to assess some of the benefits that way.
Okay, great. Here's a question. What analysis has been performed on the cumulative benefit of all the research developments? In other words, you know, would the goals be met if all activities were fully successful?
Yeah.
So
Arthur?
Sure, yeah, go for it.
So we work with Georgia Tech as an independent assessment of our technologies. So we have been working with them for, I guess, over a decade now. And so they're looking at collectively with all the technologies being developed under CLEAN Phase 1 and Phase 2. And of course, they're going to be looking at CLEAN Phase 3 as well. And we do have some charts. I'm not sure, Arthur, did we have it in the backup slides?
We do. I could pull that up.
Like how many
cars,
taking off the road, that slide. Perfect. So here, this is the assessment of our clean technologies that are conducted by Georgia Tech through our Ascent Center of Excellence, project number 37. And as you can see from the noise benefit section, which is right below the third bullet, in there it says that the clean phase 1 contributed to 14% decrease in the land area exposed to DNL 65 dB and greater. And we are still continuing the assessment on a forward-going basis. And at the same time, the technologies that we did, which is basically provided on the second bullet, it says in here that 36.4 billion gallons of fuel saved cumulatively by 2050, based on the clean phase 1 and phase 2. So that kind of equates to almost like removing 3 million cars from the road from 2020 to 2050. So as you can see, there's a lot of benefit that's being achieved from the clean technologies, and we are really grateful that we are part of this technology advancements through our work. So hopefully that answers the question. Is there anything that Arthur would like to mention?
And I'll just add on that as we progress with Clean 3, we'll be doing a similar independent assessment of how these technologies roll together to provide benefits. We start with the individual benefits, but as the technologies mature and prove that out, we roll them up. So the numbers you saw there, as Levent talked about, were for Clean Phase 1 and 2.
Okay, great. I imagine those backup charts will be shared in the package with everyone.
Yes, this should be.
Yes.
So someone asks, what was the baseline against which these potential noise benefits are measured? Are they all stage 5? Was that was there a consistent baseline?
So for the program's goal as a whole, that's relative to stage 25 dB cumulative relative to stage 5. The individual technologies you saw there, different delta EPN dB are really relative to the company's individual baseline of their current product. But as we work to roll those up in a system level assessment, we do put those all in terms of total certification noise margin to stage 5.
Okay, there's a question about the clean contact address. Is that that website that you had, or is there emails?
Yeah. If you're interested in contacting us or for information about the consortium meeting or anything else, that's just simply clean, CLEEN, @faa.gov.
And that email address is also provided on the link that's provided on our last slide. If anybody clicks there, then you will be able to see the consortium meeting coming up and how they can reach us through that, which is, as Arthur indicated, clean@faa.gov.
There's 2 more questions. Are you all still good?
Yeah, we're good.
Sure.
Okay. The speakers referred to future flight demonstrations of technology for reduced emissions and noise. Will these be a continuation of the eco demonstrator program, or are there other flight demonstrations being considered?
So I guess I'll take this one. In the case of Boeing, those are largely being planned under the eco demonstrator program and future eco demonstrators. Other companies within Clean Phase 3 have their own demonstration vehicles, and will be, if they're conducting a flight test, that would be on their own demonstration platform. Most of the propulsion companies are working towards full-scale ground engine tests.
Okay, great. And the last question we'll ask is, what were the recent changes in the supersonic research goals in light of the current spotlight in carbon footprint?
So certainly there's a lot of focus on climate within the Biden-Harris administration, and a lot of the CLEAN program helps address that through the fuel burn reduction and thereby CO2 reduction, other emissions reduction. But long-term supersonic aircraft are still moving forward, and we wanted to take a multi-pronged approach and make sure our program tries to really address all these different goal areas. So from our stance, we've tried to keep clean, certainly contributing a lot to carbon and climate issues, but also keeping that multi-pronged approach to address supersonics, especially around noise and NOx emissions as well.
Okay, well, that's all the questions, and thanks to everyone who asked. And I think we'll go back to you, Chris.
Well, thank you.
Thanks.
clearly from all the questions, the audience really enjoyed the talk, and thank you again for coming and presenting that. The next talk, the next speaker is Lorenz Vogt, who's a PhD student at MIT and is working on an Ascent project to do an optimized engine. At this point, we're running just a touch ahead of schedule. It's one of the advantages. It makes my job a little harder because if we were in real life, there'd be a few seconds taken up here and there by walking to and from the podium. So I'll just stall just a touch here. If anyone has any, remind people that if you have a question for Arthur or Levent and you think of it 5 minutes from now, you can put it in the Conference IO tool, just preface it by Arthur, comma, something, or Levent, comma, something, and then the question moderators will make sure to route it to them later. So with the logistics taken care of, now I'd like to transition to Lorenz's talk, and you have the podium.
Thank you. Yeah, so my name is Lorenz. I'm a PhD candidate at the MIT Gas Turbine Lab and Laboratory for Aviation and Environment. Today, I'll be presenting about my PhD research on the design of variable noise reduction systems for civil supersonic transport certification noise reduction. My research is funded by FAA under Ascent Project 47, and my colleagues are Prashant Prakash, Professor Stephen Barrett, Dr. Jayant Sabnis, Dr. Ray Spett, and Dr. Chun Tan. So to frame my research, let's look at the environmental impacts of supersonic transport. And I've listed 3 on this slide. First of all, we have climate change impacts because of CO2 emissions, contrails, and specifically for supersonic transport, high altitude emissions. We also have air quality impacts because of NOx, CO, and MVPM. And finally, we have noise impacts because of landing and takeoff noise, where the aircraft is closest to the people, as well as specifically for supersonics, we have cruise noise in terms of its sonic boom. So if you were wondering, how can we now reduce the environmental impact of supersonics? And we look at this question from an engine perspective, we have 2 strategies. We can look at engine design, where we can consider clean sheet designs versus derivative designs. On the other hand, we can also look at engine operations. Here, again, we have 2 parts. We can look at LTO operations and cruise operations. And so my work is focused on trying to reduce landing and takeoff noise through LTO operations. Let's now look at the benchmark for noise for supersonic transport aircraft, given in terms of its standards and recommended practices for noise certification. And it turns out that those standards and recommended practices are only developed for Concorde aircraft back in the 70s, and that these standards are not generally available for supersonic transport. They haven't been developed yet. However, the FAA is in the process of doing so, and they recently published an NPRM, or a Notice for Proposed Rulemaking, on the noise certification of supersonic airplanes. And firstly, they don't want to use any existing subsonic standards for supersonic aircraft. And so they suggest a new noise category, the supersonic level 1 type aircraft, which are small supersonic business jets. And secondly, they introduce the notion of a variable noise reduction system, which is a dynamic system that is integrated into the aircraft and functions automatically to change the configuration of the aircraft and thereby to reduce noise. And so one example of such a VNRS is a programmed thrust cutback. For a programmed thrust cutback, we're going to automatically control the throttle of the engine during the takeoff profile to reduce noise. And so the focus of my work is on the design of those variable noise reduction systems, and specifically the design of these programmed thrust cutbacks. In order to design such a VNRS, or a programmed thrust cutback in particular, we propose an optimal control approach. And optimal control is a branch of optimization where we try to find a control for a dynamical system over a period of time to optimize an objective function. And on this chart, I've shown 3 different options that you could choose. For example, one option is to just give maximum thrust during the takeoff. This option will probably minimize the time to climb. Option 2 and 3 might optimize or minimize other objective functions. And so what we're trying to do is we're trying to figure out which thrust setting schedule as a function of time do we have to apply to minimize noise. And so to do that, we cannot possibly evaluate all the possible options in the design space, because this would be computationally intractable. And so therefore, we propose a gradient-based design method to solve this problem. If we're going to write down this problem mathematically, what we're trying to do is we're trying to get a thrust setting schedule as a function of time to minimize the effective perceived noise level at 2 microphones. One microphone is the flyover microphone, which is situated at 6,500 meters past brake release. And the other one is the lateral microphone, which is the loudest of an array of sideline microphones. While doing this optimization, we also have to note that any trajectory that we come up with needs to satisfy airworthiness and certification requirements. While solving this problem, several challenges are associated with this problem. The first one is that conventional certification metrics for noise are actually unsuitable for optimal control. And I'm going to discuss later in this presentation why this is. The second one is that this problem over here, if you discretize it, is an n degree of freedom optimization problem. And this is too large to solve without using gradient-based methods. But if we want to use gradient-based methods, we require sensitivities of the noise certification levels with respect to our trajectory controls. And these sensitivities are currently not available in industry standard software. The third challenge is regarding this position of the lateral microphone. Before we compute any trajectory, we actually don't know where this lateral microphone is. So trying to minimize noise at a microphone with unknown location is challenging. And so my talk today is basically, I'm going to try to discuss my approach towards solving these 3 challenges. If you look at the objective of our work, it is to inform the regulatory authorities on the development of new LTO noise standards for the next generation supersonic transport. Firstly, we're going to identify attributes of these VNRS to minimize noise, and then quantify their noise reduction potential. Finally, we're also going to look at what is the impact of employing these VNRS, which are specifically designed for noise certification, on the noise footprint, the community noise footprint around the runway. So let me now get into the mathematical models that I've developed to do my research. Firstly, I developed a takeoff trajectory model, basically defining a reference trajectory composed of 5 phases. The first phase is a ground roll phase where the aircraft accelerates to rotational speed. The second phase is a rotation phase where we rotate the aircraft until we get 0 net upward force. Then we climb until we reach the obstacle height. And from that moment onwards, we can start using our VNRS, controlling our engine thrust as a function of time until we reach our flyover microphone. After that, we're going to keep climbing until we reach a designated altitude at reduced thrust level. So this is our cutback phase. And as I said before, any trajectory that we come up with needs to satisfy these airworthiness and certification requirements. One of them is maintaining a climb gradient of at least 4%. Another one is maintaining steady level flight with 1 engine inoperative. So this trajectory model definition, I implemented that using the NASA Dymos package within NASA OpenMDAO. And so Dymos is an optimal control library that can be used to solve problems with ordinary differential equations. And it uses an implicit collocation approach as opposed to an explicit time integration approach. After implementing the model, I verified my implementation with a takeoff trajectory that was computed by Jeff Burton at NASA using flops. And so in this chart, you see the flight path parameters and engine parameters for the two trajectories, one that is computed with my model and the other one from the SDCA. And so in general, you can see good agreement between the two trajectories. There's two main differences, which are first related to the engine, because NASA and our team had a different engine model. The thrust setting to match the net thrust curve is a little bit different. And the second difference is with respect to the angle of attack. This control law for the angle of attack is computed using different methods. So we see very slight differences in the angle of attack and the associated climb angle. But in general, we have good agreement. The second model that I've developed is an open source aircraft noise estimation model, which is currently available on GitHub. This is also developed within OpenMDAO. And this model is based on semi-empirical methods from the NASA ANOP theoretical manual. Basically, what this model is doing, it uses these semi-empirical methods to compute noise sources for the fan, core, jet, and airframe. And then it propagates these noise sources to an observer on the ground using different propagation modules. And finally, at the observer, it computes the noise levels given by the ICAO Annex 16. Similarly to the trajectory model, we also verified our model by comparing our noise results with the noise results for the SDCA. These results basically compare the model, the PINA or Python noise assessment, to the NASA ANOP code. And if we look at both microphones, we can see the PNLT curves for the lateral and flyover microphone have very good agreement, as well as in terms of EPNL, we can see that on a total level, we have a maximum difference of only 0.2 EPN-dB between PINA and NASA ANOP. So this basically proves to us that we can use this model for our research. Then, as I mentioned before, we want to use gradient-based optimization to start designing our takeoff trajectory. So to do that, we need the sensitivities of noise with respect to our trajectory controls. And so here I'm going to talk about how I implemented these sensitivities for both modules. First, we have the trajectory model, which is governed by relatively simple flight dynamics equations of motion. And so computing partial derivatives of these equations is relatively simple, and you can do it analytically and just implement them explicitly in your code. Whereas for the noise module, these equations are longer recipe-like modules with lookup tables, which are a lot harder to analytically differentiate. And so therefore, I used automatic differentiation in Julia to compute these partial derivatives. After computing both of them, we can apply the chain rule, and basically we get this sensitivity or this partial derivative of how does EPNL change with or control or thrust setting as a function of time. After having these derivatives, we put both of these models in an optimal control framework that I've shown here using an input-output diagram. So if we have an initial guess for the engine thrust setting, we put that into our trajectory model. We can compute the flight path parameters and engine operational parameters. Then given an observer location, we can compute the noise at that observer, and basically we get out the sum of our lateral and flyover noise. And then we iterate on that thrust setting using our gradient-based optimizer to finally achieve our optimal thrust setting as a function of time, this TS star. And so this is the optimal control framework that I'm going to use later in the presentation to design the VNRS. Now I want to talk about the first challenge that I identified in the beginning of this presentation, namely that these conventional certification noise metrics are unsuitable for optimal control. And here's the reason why. If you look at a time step Ti, then the domain of influence of a control parameter at a time step is all the times bigger than Ti, because in your trajectory, you can only influence the future of your trajectory. You cannot influence the past of your trajectory. If you look at the definition for the current noise metric, the EPNL, it's given by this equation in terms of the antilog of PNLT. And we're going to integrate that between two time steps. This is indicated by this blue shaded region over here. We integrate between the PNLT where, or the times where our PNLT is bigger than the maximum PNLT minus 10 dB. So you get this blue shaded region over here. So the domain of dependence of EPNL are all the times between T1 and T2. So if you compare this domain of influence and domain of dependence, what you get is this region of undetermined control, which I highlighted over here in orange. Basically, in this region, you don't know what to do with your control parameter to affect your objective function. And so a simple change is, or a simple solution to that is just by changing the integration bounds to include the entire trajectory instead of only the times between T1 and T2, you can avoid that. And the domain of dependence of this integrated PNLT is therefore the entire trajectory. The reason why this works is because the tails that we are including by doing that are by definition an order of magnitude smaller than the peak of this curve. And so this is an approximation that you make, and because these tails are so small, the approximation is quite good. And this brings me to the results of my work, or the preliminary results, because this is still definitely research in progress. The first result that I want to show is regarding the second challenge that I identified. Before solving an n degree of freedom program thrust cutback, I wanted to solve a simpler problem, which is a single thrust cutback trajectory, which is only governed by 2 degrees of freedom. And this is the state of the art. And we can solve this, this problem by just sampling the design space, or in optimization terms, you use a gridding approach. This single thrust cutback trajectory is governed by, first of all, a cutback altitude, and secondly, a cutback thrust setting. Because first you use maximum thrust, and then you go back to your cutback thrust setting. And so if we sample the design space for those 2 design parameters, we compute lateral flyover and total takeoff noise, we can see that if you want to minimize lateral noise on its own, you need to be at the bottom left corner of the design space. Whereas if you want to minimize flyover noise on its own, you need to be at the top left corner. So if you sum both of them up, you basically get 2 local minima in the design space. And this means that you're always trading one for the other. So if you choose control parameters at the bottom, you're trading in flyover noise, and if you choose them at the top, you're trading in lateral noise. So basically what this means is there's always this inherent trade. And so our hypothesis for our program thrust cutback is that by using a higher degree of freedom thrust setting, we would be able to eliminate this trade between lateral and flyover noise. If you look at our results, the best trajectory that we obtained was 180 EPNdB. And for this trajectory, after we have computed it, we can also look where is the lateral microphone for this trajectory. And we found it at 2,150 meters past brake release. And this will be important later. Because now what I want to talk about is this third challenge, basically related to this position of the lateral microphone. If we look at our objective, what we want to do is we want to compute an n degree of freedom thrust setting, and we want to compute the lateral microphone at the position of maximum sideline noise. Before doing that, I tried to solve a simplified problem where I do solve an n degree of freedom problem, but instead of taking the maximum sideline noise location, I choose a predefined location, the X spec. And here in this problem that I'm going to show next, X spec is basically the 2150 that I obtained from this problem. So this one, the semi-PTCB, I'm now going to solve using my optimal control approach that I talked about. If you look at the results of these trajectories, we can see two main features of the semi-PTCB trajectory. The first one is the angle of attack, which is larger at the end of the rotation phase compared to the single thrust cutback trajectory. And this is mainly to start climbing faster and try to gain potential energy. The second feature is related to the thrust setting schedule, which is for our semi-PTCB, it is characterized by a thrust reduction and then a thrust bump. Basically, what this thrust reduction is doing, it is reducing engine source noise close to the lateral microphone, and this thrust bump is used to start climbing to higher altitudes using that thrust and to basically gain altitude above the flyover microphone and thereby reduce propagated noise. So now what we have to do is we have to check if our assumption that we have chosen this predefined microphone is good, and we basically have to see where would the actual lateral microphone be. So in the next slide, I show basically the entire EPNL along the entire sideline. And if you look at the blue trajectory, which was our single thrust cutback, you see that it is maximized at this 2150 meter. If I now specify this position in the semi-PTCB trajectory, you see that my control results in lower noise at this location, but any other location on the sideline is not taken into account in our objective function. So that's why this thrust bump basically puts noise downstream, and basically this results in a discrepancy between the specified microphone location and the actual lateral microphone location. So if you look at the total takeoff noise, if you compute it using the specified lateral microphone location, you actually get a reduction of 3.7 EPN dB. But if you look at the real lateral microphone location, we get about 2.9 EPN dB increase. So this semi-PTCB trajectory is actually not better than our single thrust cutback trajectory. But what we do learn from it is that we can use optimal control and gradient-based optimization with acoustic objective functions to design takeoff trajectories. However, our problem formulation of the semi-PTCB trajectory was not sufficient yet to minimize takeoff certification noise levels. And this brings me to the final part of my results, which is my real objective of designing a real PTCB trajectory by taking the maximum sideline noise location into account. And this I haven't completed yet. I'm still doing research on this, but my approach to this would be to, instead of specifying only one microphone, I'll just specify a series of N microphones at the sideline and then aggregate all of their noise levels into a single constraint, basically the microphone with the maximum noise on the sideline. And this aggregation of the maximum, you can use a KS function to do that. And the solution of this problem will approach our real solution when N goes to infinity, theoretically. However, computationally, obviously, you cut it off at a finite N. And so I'm still doing research on trying to get this optimization to work. The next topic that I want to talk about is what is now the impact of using this VNRS or using this PTCB that is specifically designed for certification noise on the community noise in terms of the noise footprint. And so on this chart, I've plotted 3 noise footprint areas for 3 trajectories. As a reference, I put a no cutback trajectory in gray, and then the blue and the orange are the single thrust cutback trajectory, and the semi-PTCB trajectory. And so for the semi-PTCB, what you can see is that you have an increased noise footprint between lateral and flyover microphones. And that's mainly because of this truss bump that we saw earlier in our control parameters. If we look at downstream of the flyover microphone, we see that we have a reduced noise footprint. And this is mainly because we have already climbed higher at this location compared to the single truss cutback trajectory. And because we're now higher above that flyover microphone and above all these other positions, we have a reduced noise footprint over here. But if you look at the total area, what you can see is that there is a larger net noise footprint for this semi-PTCB trajectory. And so we also want to still do further research in this area to try to understand if trajectories that are optimized for best noise certification, if they're also aligned with trajectories that have minimal noise footprint on the ground. So this brings me to the summary of my talk. First, we have developed this gradient-based optimal control framework to design variable noise reduction systems for supersonic transport as a combination of a takeoff trajectory model and an aircraft noise estimation model. Basically, this model is an enabler for discovering new operational spaces, as we've seen in this presentation, but you might as well couple the aircraft noise model to an engine thermodynamic cycle model, for example, to try to design your engine thermodynamic cycle to reduce noise. Secondly, we have also developed this new noise metric specifically for optimal control. So we went from ePNL to the integrated PNLT. Then we've looked at a semi-PTCB takeoff strategy to minimize noise at predetermined microphone locations. And we saw that our truss schedule was basically consisted of a truss reduction and a truss bump. And then finally, we also saw that our semi-PTCB trajectory formulation was actually not sufficient yet to minimize cumulative takeoff noise, and we have proposed research in this area. Finally, I want to acknowledge, first of all, the FAA for sponsoring my research under Ascent Project 47. Then Dennis Huff, Jeff Burton, Justin Gray, and Daniel Ingraham from NASA Glenn for their tremendous help in the model development. And also Adrian Bukowski from Gulfstream for his useful insights on aircraft noise certification. And finally, Ralph, Laszlo, and Mooney from FAA for their supervision and guidance on the Ascent project. So I hope you found my talk interesting. I'd appreciate any comments and feedback, and thank you very much. I'll be happy to take any questions.
Hey, thanks, Lorenz. There's one question. I have one also that I'd like to know. Do you envision this kind of optimization taking place, once while the aircraft's being designed and the FADEC being developed and such, or would this be something that could be done with each departure?
I think, at least initially, I think you should design it beforehand. But I think once the computations, maybe if you can do it faster and in real time, you might do it for specific departures at specific airports, where instead of your noise certification level, you might be able to take into account like the population density around your airport and try to optimize based on that. But I think that would be pretty far into the future.
Okay, thanks. So the question in the IO tool is that well, I'll just read it. I note that your propagation model assumes spherical spreading for supersonic capable and thus highly directional engines. My research indicates this is a false assumption even at stage 3 thrusts. And when will this be challenged and corrected by data? So I know the noise source models they do include some directionality. Do you have any comment?
Yeah, I think like in my noise model, I use directionality as well next to spherical spreading. They're just like, I think in my slide, I listed different propagation modules, all the ones that are combined into the complete total propagation of the noise from the source to the observer. So spherical spreading is one effect, but definitely like directionality is another effect. Ground effects, lateral attenuation effects, like all of those are added up in, to basically get a total propagation effect from the noise of the source to the observer.
I could ask one more question if that's okay, Chris.
Oh yeah, we still have time.
All right. So I appreciated the note about the noise metric being unsuitable. Do you think there's your research could suggest a novel noise metric that might be better suited to optimization, like the footprint? Would you get a different result if you optimized on the footprint instead of VPNO?
Yeah, I think optimizing for minimum noise footprint would definitely be interesting. I'm going to add a note that I think it would also be computationally challenging, because if you optimize for certification noise, the good thing is we basically, by doing noise certification, we make a simpler assumption by saying, oh, there's only 2 microphones that you care about. So that's actually good for your computation. You only have to compute noise at 2 locations. Whereas if you want to compute a noise footprint, then you have to basically take every location around your runway center line into your objective function, and it might be computationally pretty hard. But it would definitely be interesting if you have the resources.
I was thinking that, well, I'll just jump in here. I was looking at the plot where you had a green curve, a blue curve, and an orange curve, and I forgot the acronyms precisely. But the point was that when you had it optimize away from the one cert microphone, it managed to do that, and it pushed the noise downstream because of the thrust push. And then you were talking about using some N microphones, but isn't that sideline envelope going to be a relatively smooth function, so that you could have a few microphones and just fit a function through it, and then just say, all right, where's the max of that function? I may not have a microphone there, but I can figure out what the maximum would be, and that would be cheaper. So similarly, you could do that for the footprint.
Okay. Yeah, that's true.
Right. Possibly. It's easy to do this. It's hard to do the calculation.
Yeah, I think you make a good point where you can have a few characteristic microphones around your runway center line, and then fit a function through that, and then get your footprint through these few microphones. I think you'll definitely need more than 2, so it will at least become a little more computationally expensive, but you won't need, I mean, it depends on how accurate you want it, obviously. The more microphones you're going to put, the more precision you're going to get in your answer.
Can I ask one more question?
Well, I have one follow-up, and then I'll be quiet. Is this something that, while expensive, is easy to parallelize, or is this expensive and serial?
No, I think like the levels, like basically what the model does, it can compute noise levels at every microphone so that you can parallelize. It also computes the gradients of noise at every microphone for your objective function, so you could parallelize that as well. So basically, I think all the noise part you can parallelize, whereas the trajectory part needs to be done, I think, in serial with noise.
Okay, the last question I would like to read from the IO tool is there a direct causality between thrust and noise metrics?
I think if I understand this this question correctly, I think the causality is like if you increase thrust, then your source noise is going to increase. So basically, by increasing thrust, for a given engine, you're gonna mainly increase jet velocity, which is the main driver for the noise for supersonic engines, at least. And so, yeah, your source noise is going to increase. But that's kind of the interesting part of this research, that the increase in source noise can be balanced by a decrease in propagated noise if you are going to climb higher because of that thrust. And so that's why you exactly get an optimization problem. Is basically you have two competing effects. Increase in thrust gives you more source noise, but it can also help you to get away quicker from the flyover microphone. And so that's why I think this research is interesting to pursue.
Okay, thank you.
Yeah, real interesting stuff. We have reached the point in the agenda where we have a break. And so if everyone could take a 20-minute break, we will reconvene for 10:35 Eastern Time, and Brenda Henderson will be giving us an update on a planned Learjet test to collect some noise. So 20 minutes, and then we'll be back. Thank you, everyone. Welcome back, everyone, to the Acoustics Technical Working Group meeting. Oh, I can hear myself. That's a major mistake. I'm Chris Miller. I'm the Master of Ceremonies for this morning. The next talks will be on jet noise. The first talk will be by Brenda Henderson of the Glen Acoustics branch. Before we get to that, I want to remind people that we're taking the technical questions in the Conference IO tool. Those can be entered at any point, and in fact, if you think of a question after the next speaker has begun, you can put one in, but give us a hint that you're referring to, say, the talk by Brenda Henderson, and then we will route those questions on to the speakers, hopefully for an after the events summary of responses. The presentations and the responses will be hopefully available in about 2 weeks. We give the authors a chance to fix any remaining typos, and then we'll consolidate the package. If you've registered, you'll be getting an email from us on how to do that download. So with that, I want to say thank you for your attendance, and I'd like to turn over the virtual podium to Brenda Henderson to talk about a Learjet test.
All right, hopefully you folks can see this and you can hear me. So the last time I gave you a Learjet flight test update, my partner in crime was Dennis Huff, but he has retired. And so Leonard Holtgren has now joined the team, and Devin Boyle will be working on the weather station measurements. I've shown this chart a lot, so I'll probably go over it a little bit fast. In 2001, we had a 500-foot flyover test of the Learjet. The point of that test was not for what we are using it here. It was really looking at Chevron technology. And as such, it didn't have an instrumented exhaust, and the GPS wasn't working, so we didn't really know the location of the aircraft, but we did the best we could with that data. And then in 2018, we made a scale model nozzle of the Learjet, and we went into our Apple facility and tested it on our NATAR rig. And so what you're seeing over on the left are comparisons between the EP&Ls computed from the flight data and those we got from our prediction modules, the SAE module and the Stone 2 module in ANOP, as well as our data that we took in the tunnel labeled NATAR. So in all cases, what I'm showing you is the difference between the predicted or measured data and the flight data. In all cases, the flight data EP&L levels were above either the SAE or Stone predictions or our NATAR data. The Stone 2 produced levels that were the closest to the flight data, but quite far off of our tunnel data. SAE compared better to our tunnel data. What I want to remind folks, though, is that we didn't have a well-instrumented aircraft or exhaust because the intent of that 2001 test was something very different. So what we're ultimately trying to do here is improve our ability to predict takeoff noise for future supersonic commercial aircraft. Probably the next supersonic aircraft that are going to be out there, commercial aircraft, will be biz jets. They're looking like they're going to have fully mixed exhausts, so single stream predictions are going to be important. So we want to improve our ability to make those predictions. So this has really occurred in 2 parts. The first part was to take the data in our tunnel and to develop models for that data. I presented those models back at the last technical working group, so I'm not going to go over them here. But you can look back at that last presentation. So now we're in the second step of the project where we want to get flight data from a well-instrumented aircraft and look at how well that compares to our data, which is, and then that would also mean to our models. If we have to come up with flight corrections, we will do that based on this data set. So I've shown you this chart over a few years, but it looks different this time because note that we have a contract actually awarded. Instead of just talking about what we want to do, this is what we're going to do finally. So we got the contract awarded about 2 days before the end of the fiscal year. We have a flight test planned right now for July of 2022, which puts the pre-flight test in June. And then we're going to have a follow-on scale model test again in our tunnel following that, because we'll have the actual flight data and know how to run the conditions in our tunnel. Everything in red right now, we're hoping to move forward. We really would like to have that flight test in June. All right, so the aircraft is going to be operated and instrumented by CalSpan. The engine pressure ratio, exhaust gas temperature, and engine RPM will be recorded for both engines. One engine will be at idle, the other will be powered. That's very similar to how we ran it the last time. The data is going to be recorded with GPS timestamps, because we've got to be able to compare it to what we are measuring on the ground with our microphones array. That will also be GPS timestamped. The flight trajectories fall into two categories. The first is a steady 500-foot flyover. We found last time when we did that, we could hit the lower EPR at about a Mach number of 0.3. And then to get higher EPRs, we found out we had to lower the landing gear and deploy flaps, which created other noise sources. So thanks to Eric Nesbitt at Boeing. If you're listening, I want to thank you for the conversation that we had after the last TWG, because we're going to have an alternate flight path, that trajectory that will also allow us to climb if needed, so that we can lower the flight speed and get it into a range at the higher EPRs that we can test in our tunnel. We're going to use a linear microphone array. I'll talk about that in a minute. Our flights will occur at Niagara Falls International Airport, where CalSpan is located. We took background measurements there a couple of years back, and it looked like we were going to be able to make these measurements at that location, because the Learjet does make a little bit of jet noise. So it will be well, high enough above our background levels for this to work. On the NASA side, we are going to equip the aircraft with our own IMU and differential GPS system, and we're going to log that and also GPS timestamp that. We are going to have a ground plate array. We're not going to be using any microphones on stands, because this is not a certification test, so there's no reason for that. The array is going to be located directly beneath the flight path. Last time we had a left, a center, and a right array, and the left and right, for our purposes, were probably not necessary, so we're going to stick with the one directly below the flight path. Microphone data will also be GPS timestamps, so we're going to be able to sync that with what was going on with the aircraft. Atmospheric conditions, we're going to record up to 500 feet, and I'm hoping about 600, because with the climbing trajectory, we will be going a little bit higher. We're going to be able to get layered data, and we're still planning on doing that with the drone, and we are working with Langley to get those measurements made. The pre-flight test is going to be used to determine the exact engine and flight speeds that we can achieve. We want everything to remain below a Mach number or at a Mach number of 0.3, because we want to be able to replicate those in our tunnel and have pretty good signal to noise ratios in our tunnel. The jet exhaust conditions are going to be from the mid subsonic range to the low supersonic range, and that's just because that's what our system studies have shown would be the appropriate range of speeds for our application. And as I mentioned before, it looks like the background levels are okay at that airport, although we did have issues with crickets near the boards, microphone boards. So we are going to have a cricket mitigation strategy if we wander into the July timeframe. So that's why we kind of want to hit the June timeframe for the flight test. And those who have had to deal with crickets by ground plate microphones know what I'm talking about. All right, so after we're done with the flight test, we're then going to have to go back into our tunnel and replicate the conditions that we had in our flight test, so that we are comparing the same types of data. We really have two models. One is a true single stream jet, which I'm showing in the upper right corner, and the lower right corner is a Learjet model. The Learjet model, while it's a single powered stream, there's a secondary nozzle wrapped around that single stream. It's not powered. There's a NACA scoop on the front of the nacelle, brings in cooling air, and then it exhausts through that secondary stream. So it's there. It extends a little bit beyond the primary nozzle, but it is not powered. So we'll run both of these nozzles in our tunnel. Exit diameter is 3.56. The reason we've used that is because that's about the equivalent diameter of a lot of the nozzles we've used in the past. We want to be able to find out our ability to predict with the way we take our data. And so we expect that to occur, as I showed in that earlier schedule, still in this fiscal year, but a couple of months after the flight test, because we're going to have time to process the data. With that, I will take questions.
Hey, thanks, Brenda. And just a reminder to anybody, go ahead and type up questions. I know it takes a few moments. So I had a question. How many flyovers do you anticipate having time to perform?
I think we would like to repeat each data point 5 times. We cannot predict exactly how many flight points we can get until we do the flight pre-test, because we've got a range of VPRs we want to fall into, and we don't know what they're going to be able to do and what Mach numbers they're going to be able to hit. In the past, we had about 4 to 5 speeds that were of interest times 5, so maybe 25 flyovers. Roughly speaking. The pre-flight will tell us more.
Okay. And will there be anything sensitive or proprietary about this data set, or is it something you ultimately plan to publish, distribute, and such?
So that is a really great question, David. This is for the public. We all want to know how well we can predict flight data. So ultimately, this data is going to be released, our tunnel data is going to be released, and our models are going to be released. And that's why I appreciate the help I've gotten previously from folks at the ATWG. They've given me a lot of help of how to do this test better. And so hopefully everybody will benefit from this when we release it.
Okay, that sounds good. I don't see any questions in the IO tool, but if, like Chris said, if anybody else thinks of one later, feel free to type it up and just mention that it's for Brenda. Back to you, Chris.
So, well, I'm going to get one in there. Is there's one that showed up for Brenda, but I'll do that. If you could go to slide 5, Brenda. So you talked about the point of the climbing trajectory is to have a higher engine power setting, but the same flight speed. Is that right?
Right.
Okay. Even though the distances are messy, we'll have GPS coordinates, so that won't be an issue.
You can have everything, right? So you pick the one thing
okay.
that you should know the best, which should be the location of the aircraft because of the GPS. So that's a great question.
So this is with flaps up, wheels up, clean airframe.
Definitely wheels up, and we are really hoping the flaps can always be up.
Okay. Oh, now there's questions.
Do you want me to ask one or two of them, or would that be all right? We have
2 minutes. Sure.
I talk fast.
Okay. Could you elaborate a little on using a drone to measure atmospheric conditions?
Can I elaborate? Not yet too much. We will probably present that in April to ATWG. We have the similar instrumentation to what's used on a weather balloon. We're going to give it a try by flying it out at Langley. We want to suspend it further below the drone to make sure that we don't have any local pressure gradients or downwash issues. And we might go ahead and use something like the temperature string that is used sometimes on the weather balloon and just have a string that's run up. The details of that, I promise you I will present as soon as we have worked out all the details and done some pre-flight tests in April, because I know everybody wants to know if it's going to work. We won't use the drone unless we have shown in separate tests that it really does work the same as the weather balloon measurements. If it doesn't work, we're going to go back to the weather balloon. I'll keep you folks posted.
How about one more?
All right. Will the wind tunnel test simulate any reflecting or scattering surfaces of the aircraft or include any of noise reduction devices?
Not this fiscal year. If that changes in a future fiscal year, I will let you know. But this year is only going to focus on repeating the engine conditions and just a clean nozzle.
All right.
Well, good question.
Yep, there's some more questions coming in, so that's great, and that's going to be, I think, part of this format.
Yep, and we'll forward those on to Brenda for written responses. So now I'd like to switch. The next speaker is Will Banks, who's at NASA Glenn in the Inlets and Nozzles group, and he's going to be talking about some parametrics aimed at optimization.
All right. Hi, Chris. I apologize. Let me get my here. Let's see.
I'm seeing it.
Okay, great. I think Raj. I think Raj is sharing his screen.
Oh, would you like the slide share? Will?
Yeah, that would be awesome. Am I allowed to do that?
My apologies.
That's all right. That is okay. Yeah. All right. Chris, is this showing up for you?
Loud and clear. I can see it. I can hear it. So.
Okay. All right. Well, as Chris said, thank you very much. I'm Will Banks. I'm a contractor with HX5. I'm working with the Airport Noise and Commercial Supersonic Technology Project. And today I'd like to share my parametric mixer design process supporting the acoustic explorations for internally mixed dual stream nozzles. So last year, CST started a new focused research effort, which we internally called Tech Challenges, to address prediction uncertainty in supersonic aircraft. While our databases informing empirical models are extensive for conventional aircraft, supersonic aircraft require components with different configurations. We have little data for this, so this leads to a much larger prediction uncertainty. Little chart to help you along there. Ideally, this would be addressed via scale model testing of the relevant components, but fiscal and facility and limitations make this impossible currently. So the Prediction Uncertainty Tech Challenge aims to use matured physics-based simulations, or PBSs, to produce the required data for components relevant to industry partners in the near term. This approach requires some high fidelity designs of likely supersonic propulsion components. A two-stage fan was designed by NASA by GE for NASA, but we are doing the exhaust system and nozzle system in-house based on OEM input. So some design requirements for the near-term supersonic exhaust nozzle. So while a fan design is being produced by GE for NASA, the existing exhaust nozzle technology is expected to meet noise requirements, but has not been acoustically tested. So we are developing our own design in-house. To keep it relevant for near-term application, several design requirements are considered. The focus is on acoustics at low takeoff. Good thrust performance must be kept at supersonic cruise for full mission consideration. A high-performing mixer helps in this pursuit. And as a sound mixing process typically results in thrust augmentation and noise damping. An external plug is being investigated on the nozzle end to reduce boat tail angle, requiring an internal mixer design, while low complexity is desired for a slew of reasons. To this end, some goals for the mixer design specifically were to limit the initial design space to a manageable number of parameters for optimization studies. We'll focus on the aero and thrust performance first, with jet noise reduction efforts undertaken once an adequate understanding of aero performance is achieved, and we have some optimized mixers in our database. Thirdly, we want to use automation methods as much as possible to allow for on-demand generation of mixer designs for aero and acoustic analysis. So while the literature on mixer design is somewhat sparse, especially for supersonic applications, we have a few shining beacons to guide us through the dark. As part of the Energy Efficient Engine Testing Program, Kuhar and Chamberlain produced a 3-phase study examining various mixer geometric parameters, including lobe count and penetration, which we examine here, and provided valuable response parameters in the form of mixer effectiveness and mixer pressure loss coefficient, which we also use here. Those encompass the first 3 references here. Finally, more recently, Allison, now Rolls-Royce, and NASA Glenn conducted extensive testing in the late 90s of several mixer configurations of subsonic conditions to populate a design database. While these tests were primarily acoustics oriented, some thrust data was collected as well at ASE Fluidyne. So these tests serve as a reference point for the current study. And additionally, I'd like to thank Jeff Burton's internal document detailing theory and calculation of ideal thrust and mixed flows that has proved integral to some of our more complex performance parameters and analysis. Flight conditions for this study were taken from a 1D analysis performed on a NASA-designed 55-ton 8-passenger STCA, which was itself created to provide preliminary acoustic prediction data to ICAO. During the supersonic cruise mission point, the paper airplane would fly Mach 1.4 at 50,000 feet with a bypass ratio of 3.33 and an average nozzle pressure ratio of 5.89. At the outset of the current study, the goal was to match the bypass ratio, extraction ratio, and area ratio to the STCA, but it quickly became clear that matching these figures from a 1D analysis was not feasible in the 3D RANS environment. For those kind of wondering what extraction ratio is, that's this ER parameter, which is inflow total pressure in the bypass to inflow total pressure in the core. It's determined that bypass ratio is the most important condition to match. So this chart on the right here shows our it's created using a simple axisymmetric splitter in a dual stream nozzle to assess the impact of both area ratio and extraction ratio on bypass ratio. While extraction ratio can be fixed through boundary conditions and area ratios can be fixed through geometry, shifting mixer designs impact flow characteristics and thus the bypass ratio. So a small area ratio of 1 was selected as this produced a flatter response curve. Note the black response curve here. It's much flatter, much more stable than the other two. This lowered the variability of bypass ratio between cases, just bringing consistency to the study. Extraction ratio and area ratio were thus held constant through the entire study. Moving on to nozzle geometry. To isolate the impact of mixer performance, an academic dual stream nozzle was designed to house the various mixers considered. This nozzle has a few key features. Areas A6 and A16, core and bypass area respectively, were equal to maintain an area ratio of 1. Area A7 was set as the sum of A6 and A16 in order to keep the in order to exclude the effects of expansion or contraction on the mixing process. The center body down here was contoured through the transition region to account for mixer thickness, seen here. Areas A8 and A9 were sized to create a CD nozzle, which ideally expands flow to free stream conditions. Length L1 was kept constant regardless of mixer length, and I'll go into how that happened or how we did that in a second. Length L2 was purposefully extended to about 3 times the length of L1. This helped us visualize a more complete mixing process rather than a more application accurate short mixing length. Length L3 finally was sized to avoid separation in the CZ nozzle. This geometry was held constant throughout the entire study, with dimensions shown remaining unchanged throughout, regardless of mixer geometry. So, moving on to the actual mixer geometry, several design constraints were applied to address the stated mixer design goals and keep as much possible as consistent from case to case. 2 profiles were generated from 5 parameters considered. The 5 parameters considered that fully defined the mixer surfaces. First, the trailing edge profile was defined perpendicular to the nozzle centerline at an axial distance of x equals 20 inches, with set peak and trough radii. So that, you can see RP and RT as the peak and trough radii in this diagram here. RN is the nacelle radius, and RS refers to the splitter radius. The mixer extends upstream a length of L from this trailing edge to a simple axisymmetric splitter, seen here. So this is where the mixer trailing edge plane occurs. And then L extends upstream down here rather than downstream. This extends upstream to a junction with an axisymmetric splitter, which bifurcates bypass and flow inflow streams. A parameterized cubic spline, seen here, defines the transition from splitter to the trailing edge, and the slope of this line at the junction to the splitter was set to 0. As far as the actual parametric space is concerned, there were 5 parameters, as I said before. To satisfy these constraints, the parameters were defined as such. The first is lobe count. I think that's pretty self-explanatory. Mixer penetration is a normalized quantity describing how far the peak radius extends from the splitter toward the nacelle. So how far this RP value extends between RS and RN, and that was defined as a percentage. Lobe bias was a coefficient which shifted the lobe width toward the peak or the trough, or positive or negative values respectively. So positive value shifts thickness up to the peak, negative value shifts thickness down to the trough. Mixer length defined for the trailing edge, from the trailing edge to the splitter junction, as I stated previously. And then trailing edge slope, which is the spline slope at the trailing edge. While this was kept at 0, this was variable to give us a 5th parameter. Something I want to keynote here is that the trailing edge profile is defined to always keep an area ratio of 1, regardless of parameters. Now, that was done using an integration-based method while defining the radius on a polar coordinate system. That was integral to keeping everything consistent, keeping our bypass ratios near, or hovering near 3.33. Just to give you a couple examples of what the parametric space actually looks like. Here's got a diagram showing how the trailing edge profile shifts through the range of penetration and lobe bias figures. You can see as penetration increases from 50 to 70%, the lobes encompass a higher portion of the available area, being the area between the I guess the center body and the nacelle out here. It's a small footprint here to a larger footprint here. And as lobe bias increases, the width of the lobe peaks also increase. So that's most noticeable on the, I believe it's on the 50% end here. So for a negative lobe bias, you can see it's a roughly equivalent width for the troughs and the peaks. And as that increases, this width down here is seen to sharply decrease, while the width in the peak lobe is it's wider. Moving on to the spline profiles examples. This diagram shows how the spline profile shifts through the range of mixer length and trailing edge slope values. As mixer length increases here, the portion of the bifurcation the mixer encompasses increases. So you can see for every length, the mixer extends out to this 20-inch mark, but what's changing is the length of the splitter upstream. So the inflow plane is always here, the trailing edge plane is always here, but depending on the length of the mixer, the actual length of the splitter changes to accommodate. As trailing edge slope increases, the mixer transitions from a curled-in profile at negative trailing edge slope, so where you can see that negative 0.5 slope comes into play, to a flared-out profile at the trailing edge. So at a positive 0.5 slope, that is seen to flare out dramatically. Now this has led to a few separation issues, and predictably the low trailing edge, or the negative trailing edge slopes, tend to shoot flow back into the stream. We'll see why that's a problem in a bit when I show some results, but for now, go ahead and show you some sample cases of the full parametric space in action. These 3 sample cases shown here kind of show some of the range of cases that were run, with resultant 3D surface contours shown to the right here. The trailing edge slope and spline profiles seem independent in the 2D world, but you can see they're significantly intertwined when we move to the 3D world. So it moves, as we move to a smaller mixer, you can see how shifting these parameters slightly results in very different mixer design profiles here. Moving on to the computational approach, don't want to go into too much detail, but I'm happy to if anybody has any questions on these after the presentation. So it's a basic 3-step process from mixer geometry creation, grid generation to numerical solution. It's all procedural, meaning every step was the same, and it was as automated as it could be. Pointwise provided some difficulty in that regard because gridding is never as easy as it seems like it should be. But first stage was using a NURBS Python package to automatically generate a 3D surface from the parameterized profiles shown before. So The input was 5 parameters, and the output was a 3D surface for the bypass in the core region. That was imported into Pointwise, which was used to generate a 3D unstructured grid. The result was about 19 to 21 million nodes per case, which is a bit high, but NASA has significant resources with our with our NAS supercomputer out at Ames, so this wasn't as much of an issue as it has been in the past. And finally, this grid was uploaded to, or was solved in Fun3D, or the steady RANS equations. Sorry, were solved with the turbulence model of the SSTV using Fun3D out at NAS at Ames. And it took about 2,400 CPU hours per case, meaning which was equated to about 6 hours on 400 cores. Just shows, I just wanted to show some quick hits of what the contours look like for our center point case. Moving on to some approach validation. So although no thrust data actually exists for the examined configuration since I made it up, the computational approach developed was validated against AIAA's dual mixed flow reference nozzle. So back in 2016 or 2017, several organizations, including Boeing and Lockheed Martin, submitted computational approaches and results for the dual flow nozzle shown, with both a heated and cold core cases. NASA's approach resulted in NPR versus thrust coefficient curves, similar to other state-of-the-art industry unstructured CFD solvers. This comparison provided the confidence needed to move forward with the study without the luxury of experimental validation data. And you can see on the CFG versus NPR plot on the right here, these little NASA meatball markers show our data as compared to what is closest was the Lockheed Martin unstructured fine grids. I think they had an anomalous low NPR case, but we are mostly concerned with high NPRs at supersonic cruise. And it also compared well with Boeing's unstructured fine solver, shown in orange up here. So moving on to some sample results. So for the 3 cases shown earlier, can touch back on those quickly. This is what they look like on profile. The Mach number plots illustrate generalized flow patterns. So contours placed at the XY symmetry plane help orient us to the general flow field. And here we can see some Mach number plots on the left and turbulent kinetic energy plots on the right. The Mach number verifies typical nozzle operations. We have similar velocities, resulting in lower Mach numbers within the heated cores, since temperature affects speed of sound. A degree of mixing can be seen through the nozzle body, ending in choked flow condition at the CD nozzle throat, A8 here. The turbulent kinetic energy provides a footprint for turbulence within the nozzle body, one of the major mixing mechanisms. There's about 3 of them that we're closely examining. Turbulence is is probably the one that we have the best indicators for in CFD. It is evident that TK within the nozzle increases from bottom to top, so we would expect mixer 1 to show the highest mixing performance just based on this initial checkout. Moving on to total temperature. Tracking total temperature provides direct evidence of mixedness, combining velocity and static temperature to paint a complete picture. Details convection, another major mixing mechanism, and shows the greatest contrast between core and bypass streams. The same symmetry plane views from the previous slide are shown on the left, contoured with total temperature. These plots seem to back up our prediction from the TKA contours that Mixer 1 provided the best mixing performance, and this claim is further supported by the progressive cut plane contours on the right. A major observation from these plots is that Mixer 3, seen on the bottom, with its negative trailing edge slope, seems to only reinforce the divide between the 2 streams, and thus it would appear that a negative trailing edge slope is detrimental to performance. To effectively analyze performance, a few response parameters were introduced. First, we had thrust coefficient, a standard way of examining overall nozzle performance, comparing measured thrust to ideal thrust based on an isentropic expansion process. You want a higher thrust coefficient, means a more efficient process. Mixing effectiveness, as used here, was introduced by Kuhar in that series of papers detailing lobe mixers. It takes actual thrust coefficient improvement from introducing a heated core and compares it to the expected improvement based on ideal expansion. Again, you want a higher mixing effectiveness that gets better performance. Pressure loss coefficient, also introduced by Kuhar, examines total pressure loss from nozzle inflow to nozzle exit. To isolate the aerodynamic effects of the mixer, pressure loss for a cold confluent mixer, just an axisymmetric splitter at cold conditions, is subtracted from a cold flow pressure loss case with the mixer installed. This isolates the aerodynamic impact of the mixer from other things such as temperature, swirling, or nozzle geometry. So for that, you would like a lower K because you want less pressure loss. It's better for efficiency. In all metrics beside pressure loss, mixer 1 is seen to show the best performance here with the highest thrust coefficient, highest mixing effectiveness value, and the lowest, all, so I think I skipped temperature variance. So temperature variance statistically interprets temperature data collected at the mixing duct outflow plane to provide a measure of remaining variation between the two streams. We want that lower because the lower the variance, the higher the mixing. So we can see the mixer 1 provided the best performance with the flared out with a short mixer and a flared out design to more aggressively mix the flow. And mixer 3 with its bowed in trailing edge slope and long, generous profile provides the worst performance in all metrics besides pressure loss coefficient. As far as the DOE study, 3 phases of a DOE study using Design Expert have been conducted to build a parametric model of the 5-parameter mixer design space. The initial screening phase involved casting a wide net over the design space in order to whittle it down through testing of the corner points. That's the initial screening. At this stage, most of the findings revolved around what was physically impossible or numerically unsolvable. The design space was reduced to reflect this. That was continued in the half factorial phase, which involved performing basic half factorial study over the design space and using performance response data to inform further reduction of the design space. Most notably, we saw that lobe count seemed to not matter, and so we fixed that at 12 going forward. This is reflected also in literature. The quadratic response surface was next. At the first attempt to actually model the design space to produce an optimized configuration. The bounds for the study are shown below in this chart here. However, it has since been recognized that not enough points were simulated over too constricted of a range, and the model was quickly shown to be inaccurate during validation testing. So this is really informing a current study ongoing with an additional 40 points being run to bring cubic resolution to the response surface model. Finally, we got some perturbation plots just showing some of the results here. So perturbation plots for the thrust coefficient and pressure loss coefficient show a closely tied relationship between the two, despite the conflicting impact on total performance. And this indicates that the mixing process, while it provides thrust augmentation, comes at the cost of total pressure loss. So you can see as our trailing edge slope increases from its lower bound to its upper bound, for example, our thrust coefficient increases, but our pressure loss also increases. So this indicates that the mixing process provides thrust augmentation, but inherently also provides or produces pressure loss. Ideally, a peak for each of these parameters would be seen within the bounds of the study, indicating bounds that need to be expanded and the resolution needs to be enhanced here. For the final 2 parameters, response surface, the mixing effectiveness and temperature variance, you can see that these are tied closely with the previous ones. So for thrust coefficient is closely tied to mixing effectiveness, which makes sense as mixing effectiveness is a measure of the thrust augmentation within as caused by the mixer. So to conclude, the parameterized design and analysis process was created for dual stream mixers for supersonic jet noise suppression, with the objective of finding high performance mixers to compare acoustic performance between. 3D unstructured RANS analysis was used to evaluate aerodynamic performance. With the DOE methodology was used to model the parametric space from these analyses and select mixers with optimal performance. Some significant findings: little to no impact was seen from the lobe count, high impact from the trailing edge slope, significant impact from mixer length, peak thrust response from penetration was in the range examined, but it was the only one in the range examined, and so the range needs to be expanded. Finally, we have a low but significant impact from lobe bias. Going forward, we will be conducting RANS-based acoustic analysis of optimized mixers, and some additional parameterized features will be added in follow-on phases, such as cutback scarf angles, low scallop lobes, lobe vents, vortex generators, or trailing edge chevrons. And finally, we'll be integrating with concurrent work on exhaust systems. This will range from integrating a plug nozzle to examining a full emission profile. And that is the material I have. Thank you very much for your attention, and I will turn it back over to Chris.
Hey, Chris, do we have time for a question?
Yeah, let's take one question.
Okay, so the question is, how do the various concepts affect discharge coefficient?
So discharge coefficient it hasn't been examined closely in this study so far. It's just suffice to say we haven't examined it closely. That will be kind of part of a follow-on investigation, but yeah.
Okay, thanks.
All right, thank you. Great. At this point, we're going to move on to the next speaker. Chris Rusher, who works for Spectral Energies, has been involved with an SBIR to look at designing novel methodology for rapid acoustic optimization of supersonic multi-stream 3D nozzles. So the virtual podium is now yours.
Excellent, and thank you. Okay, well, thank you for the introduction. And like Chris said, my name is Chris Rusher from Spectral Energies. And today I'm going to talk to you about the work that we just finished up on a NASA Phase 2 SBIR under the direction of Dr. Brenda Henderson. So before I start, I'd like to thank both Brenda and the NASA SBIR program for working with us on this program. So just an outline of what we'll talk about here today is just a kind of a technical overview of what we're trying to do, some of the objectives we want to look at, and then we'll jump into the meat of the work, really looking at how we're predicting the acoustics so we can do the optimization. And then we'll talk a little bit about some work we did to come up with a nozzle to kind of test this, and then some of the optimization that we found, and then wrap up with some experimental validation. And I would like to also at this point thank my co-authors who contributed greatly to this, Dr. Dmitry Papamashko and his group at UCI, at University of California, Irvine. So the problem that we're trying to look at is, I'm sure everyone's aware of, is that there's this desire to have commercial supersonic transport aircraft, and these aircraft are going to have to meet all the stringent noise regulations, in order to be able to fly in the U.S. and Europe. And one of the issues is during takeoff is maybe jet noise is going to be a potential issue. So we want to figure out, can we come up with some good designs for the nozzles in operating conditions that will reduce the noise and hopefully allow these kind of aircraft to take off and meet the noise regulations. However, a lot of the current design tools that are available really aren't geared towards some of the more advanced propulsion configurations, especially what we'll focus on today, some of the three-stream type nozzles. And the kind of what the current state of the art is, we can have empirically derived models, and they can get you really quick results. But if your empirical models weren't informed on these types of nozzles, or if they don't know on the type of data that they'll be getting, then they're not going to really be relevant for the nozzles that we're looking at. And we could also do some high fidelity simulations like LES or detached steady simulations. And if you use them correctly, you can get fairly accurate results. But they end up being very computationally expensive and just really aren't feasible or practical for doing any optimization. So what we've done and what we've shown is that we could, maybe use somewhere in between. So we said, well, let's use RANs, and then we can inform that with some fundamental physics. And some of the past work that was done by Dr. Papamashko has shown that we can get some really accurate results with that. So we wanted to, in the SIBR, extend that work a little bit. And then sort of the premise of what we wanted, of what we're trying to show, what the benefit is that we can reduce the computational costs of running some of these acoustic simulations from millions of CPU hours that you might need for the LES down to hundreds of CPU hours that you might need for RAN simulation. So the way that our approach works is kind of outlined in these next two slides. But we'll start out with a parameterization. So we'll figure out what parts of the nozzle can we change, and then we'll set up a design of experiments to see how many variables we want to change, and how we're going to do that to come up with some response surface. And once we've done the design of experiments, we can get the different nozzle geometries that we want to look at, and then run them through the RAN simulations. And we can do the RAN simulation of both the internal part of the nozzle as well as the external part of the jet that'll be coming out of that. And then we can, from the RAN solution, extract out the quantities that are going to be of relevance to the noise emission, like acoustic Mach number, Reynolds stress, things like that. And we can also get the aerodynamic performance, like thrust, from the RAN simulations as well. And then we can run all the useful information through our noise emissions model, and we can develop a acoustic response surface. We can also get a performance response surface. And one thing that we would also like to add at some point is some more intrinsical type response surface to help with the integration, to make sure we're not coming up with some nozzle design that isn't possible to fly. Then we can put some weights onto there to say which of these three is more important. And then we can come up with an overall response surface. We can run that through an optimizer, come up with an optimal design, run that through the RANs, check how well that agrees with our response surface. If it's in agreement, we can be happy. We can go on to some final experiments in our LES for validation, or if not, we can plug that back into our response surface and update that and kind of loop until we're happy with the agreement. So the main tasks that we'll talk about here that we completed as part of this phase 2 were to develop and to improve the acoustic prediction methodology, and come up with an optimization methodology, and then start to look at what kind of nozzle we can use, and then to finally validate the tool with experiments and or high fidelity simulations. So the way the model works is we define this outer surface of peak Reynolds stress. And what we're saying here is that on this surface, this is really where we're capturing that convective velocity of the eddies in the shear layer that are controlling the noise emissions. And so, we're saying in this work that if we get this surface, this is really where we can start to propagate the noise from. And then once we have the surface, we can extract out some of the important elements that we will need to have into our model. And this includes the Mach number, the axial convective Mach number, and the transverse Mach number to help us understand the azimuthal directionality, as well as the Reynolds stress, and then some information about the turbulence, like the kinetic energy and the dissipation. and then the azimuthal direction of the mean velocity gradient. So those are the parameters that we need to get out on that surface. And the way that we're defining that outer shear stress surface is by first taking some points well outside the jet, and then kind of using a ray approach and tracing the gradient of the velocity until we come up to that peak location. And then once we do that, we can define this white line, which is what we're calling the outer surface of peak Reynolds stress. And then what you can see for, as you would expect for a round nozzle, an axisymmetric nozzle, we're getting a profile that looks very circular. And then when we start to add some more asymmetry in there, we can get some more interesting flow shapes in there. And so what we would do is we would take different axial locations and run this algorithm, run this procedure until we get the OSPS profile at a bunch of different axial locations. And then we can come up with this 3D model of what that surface looks like. And this slide is just showing a couple different examples of that. Like I said, you have the axis type nozzle that looks very circular. And then as you add some more asymmetries into there, you can see that that surface gets a lot more interesting looking. So now that we have that surface, we have to come up with how are we going to get the actual acoustics on there. So for that, we have a few different terms on there. We have the amplitude term, which is made up of the shear noise and the self noise. We have some 4D volume correlations here, as well as some other correlations for the axial direction, the time-wise correlations, and then some azimuthal direction as well. And then we can put that into a space-time correlation of the Reynolds stress tensor, which we can see here. And in this formulation, there's a few different closure parameters that we need to define. And these are things that we can get from some RANDs or from the previous data that we would have collected to build up this model. And so these are just showing some of the closure terms that we would need to get. And then, so like I showed a few slides ago, the spectral density, is a volumetric integral, and that might take a lot of time and a lot of computational power to compute. And since we want to be able to have this in optimization formulation, we want to be able to do this fast but accurately. So what we can do here is we can collapse that volume integral onto a surface integral on that OSPS surface. And what that means is that we might not be getting the actual acoustic values, but we do believe that since that OSP surface is going to be very responsible for where the noise is coming from, we do believe that we can look at these surface integral and at least get a good idea of what the differences are in the acoustics. So if we have some known baseline acoustics of our nozzle, we can then start to compare if what we're doing is reducing the noise or making the noise worse. So this really is a differential noise type approach. So then, like I said, once we have this model made, we've went out to do the integral on the surface. We have to start defining some of these parameters here. And the way we do that is we define a cost function. Basically, what we would have is we would need to have some RANDs data so we can start to build up all the equations that have these different parameters in there. And then we would need to have some experimental data that we could compare that to. And then we can start to fit the model from the RANS to the experimental model, or the experimental data. And then from that, we can start to get the values of some of these parameters in that vector. Okay. And so once we do that, we can go through and we can get an estimate of what the change in the acoustics are based on looking at a baseline, which for this plot we're taking this axi nozzle. And these were some results from our partner at UCI, some simulations and some experiments that they had done earlier, just to show, what kind of differences we're getting in the acoustic model versus the experiments. And we can see that in general, if we look at the right-hand side of this chart, that we are at least getting the right trends, where we could at least start to say that we're, on the right track of figuring out how we're doing in terms of acoustics. And then we see a similar thing on this slide as well. And then on the next slide, we see a similar story for a different nozzle. So based on some of these results, we were really happy with what we were seeing from the acoustic model. And then one other thing we can do is, once we have that, the delta SPL, we can come up with a synthetic sound pressure level by taking the sound pressure level for the base nozzle that we're starting with, which we would know from experiments or higher fidelity simulations. We can add that delta sound pressure level onto that model, and then we can start to do some more direct comparisons there. And what we can see here is that for this particular nozzle case in the downward direction, you can see that the actual and the synthetic are matching up fairly well. They're at least, again, showing the right trends. And we see a similar thing in some of the sideline noise as well. And one of the reasons that we want to have this synthetic SPL is then we can run this through our algorithms to get the EPNL, and then we can compare and contrast that between what we started with for our baseline nozzle and what we're getting for the optimized nozzle. And what we can see here on this particular plot is that if we look at what the actual experimental data is showing us for the takeoff monitor, we're getting around 99.6 dB for the optimized nozzle, whereas with the synthetic, or what we're getting from our model, we're getting, just about close to that, a half a dB off or so in the takeoff monitor. And then in the sideline monitor, not quite as good, but still within a dB. So we're pleased with that. Okay, so the next part of the SIBR project was to look at a relevant nozzle to demonstrate this this approach on that we developed. And these were three of the different types of nozzles we were considering for this work. And we'll focus on this uniform mixing nozzle for this presentation. And so we went ahead and we did some thermodynamic analysis to try to get what the cycle number should be based on some consultation with industry folks and with NASA, and just with the previous knowledge of spectral energies and our partner, Dr. Papamashko. And from that, we were able to come up with some cycle numbers, which we see here on this chart. Okay, and then once we had the cycle numbers, we came up with our baseline axisymmetric nozzle. And this was kind of inspired by the GE Infinity engine, which at the time we were thinking would have been going on to one of the Ariane planes. So we developed this this nozzle and came up with a way using MATLAB and SolidWorks where we could rapidly get a solid model of that and then actually have this model 3D printed so we could do some of the testing later on. Okay, so once we had the baseline nozzle, we had to figure out what parameters were we going to change to try to reduce the noise. So for this particular work, we decided we wanted to look at shaping the thickness of the third stream. And to do that, we came up with this Gaussian bump approach in a few different locations on the nozzle where we can kind of put in this waviness type thing as we're seeing in this figure here. And then we also wanted to make sure that the area of the third stream was conserved, as well as we wanted to make sure that the minimal thickness of this wasn't getting too small, as that would start to make, when we're doing the 3D printing, make that kind of stick together. And that would cause unwanted effects in the flow field and in the acoustics. And so because of those constraints, we really only have two design variables that we're using. And then we wanted to convert that from our design space into the coded variable space so we could have ones and zeros and make our response surface. When we did that, this is what our space looks like. We're doing 9 different designs for our design of experiments. And we can take these numbers, run them through the geometry that we're trying to do with the reshaping. And these are just showing on this plot and on this chart and the next chart, just the 9 nozzles profiles that we're going to be looking at. Okay. So once we had that figured out, we ran that through the MATLAB code to get the geometries, and then we ran this through a grid generator. And these particular grids had about 7 million points apiece, and then 10 diameters radially, 40 downstream, and 4 upstream. Boundary conditions were pretty standard. We had total temperature and pressure for each of the nozzle streams. The walls were no slip, adiabatic. The outer boundary was a characteristic condition. And then we were only modeling half of the nozzle, so we had a symmetry boundary condition to handle that. And the simulations that we'll show here were performed at our partner at UCI using their Parquet code. And again, this was using RANDs, and the particular model we used was the SST model, which uses the K epsilon and the K omega models. So these are some of the results that we got from running the RANDs. So these are showing the OSP surfaces for that particular nozzle. So then we take those OSP surfaces, we extract out the parameters that I mentioned towards the beginning of the talk. We run that through the acoustic algorithm, so doing the integration with all of those closer parameters. We get the change in SPL, we add the baseline, we run that through our PNL to get the ePNL, and then we can build up our response surface, and that's what we're showing here on this slide. And you know, what we're seeing is that there is in fact a optimal point where we have reduced the noise, and that is this 0.3, 0.9 based on our coded variables. And on the next slide or so, I'll show what that nozzle looks like But one thing to mention is when we did some of these calculations, we were a little bit off just due to timing. We kind of guessed where that optimal would be. So we'll be looking at this sort of sub-optimal point, but very close to the optimal point. And then the other thing we wanted to make sure of when we were going to do this is we wanted to make sure that the thrust wasn't going to be too adversely affected. And what we found is that the point that we're choosing, the nozzle that we're choosing, really only had a thrust loss of about 0.02%. And there were a few other points on our design space where the thrust was affected worse. But the one thing to point out is we're really not doing that aggressive of a design change on here, so we wouldn't expect the thrust to be that badly affected. Okay, and then so this is showing what that optimal nozzle looked like. You know, kind of what we would expect based on some of the work that, if you're familiar with Dr. Papamashko's work, you know, showing that if you have a thicker stream near the bottom, you're going to get less acoustics going down to the ground there. So this is kind of what we would have expected just based on some of that previous work. But this is kind of a nice rigorous way of looking at that. So once we had that nozzle design, we ran that through the 3D printer, and we were able to install it in the UCI facility. We were able to get some acoustic data for that that we could use for validation purposes. And then this next slide is just showing the facility and then the nozzle installed in that facility. Okay, so on this chart, we're showing the SPNL for the baseline nozzle and then the optimized nozzle that we developed. And we can see here that the optimal nozzle is in fact quieter than the baseline nozzle, especially in the more peak noise direction. And then it seems to be about even in the sideline directions. And then just the last thing to show here is we ran that through the PNL and EPNL equations. And what we were able to show is that the model was saying in the takeoff monitor, we would get a 2.4 dB reduction compared to a slightly higher reduction that we found in the experiments of 2.9. And then in the sideline monitor, we had a 1.3 dB reduction based on the model. And then the experiments didn't show a reduction in the sideline. But despite that, we thought that we were pretty close, and we were pretty happy that our model results were matching up fairly well with the experiments. And so with that, I can just wrap up with a summary and conclusion here that Spectral Energies and our partner, Dr. Papamashko, were able to develop an acoustic analogy that uses inputs from RANs. And that analogy compared very well with some of the experimental results that we found. And we were able to use that to develop an approach to minimize the noise. And then we were able to demonstrate that the approach could be used to shape what we think might be a relevant nozzle for you know, some of the 3-stream work. And so with that, I'd like to thank you for your attention, and I'd be happy to answer any questions.
Thank you, Chris.
All right. Yes, I appreciate that. So I have a question. What's the product that your company is commercializing from this SBIR that encompasses this work?
So what we're going to be trying to commercialize is putting this into a tool that could be given to, you know, some company that's trying to develop the nozzles for a future commercial supersonic commercial aircraft.
Okay. And so if I could follow that up, so what would be the input? I mean, I know in that last example you showed that the user prescribes you know, temperature and total temperatures and pressures for the nozzle inlet. What all do they need to bring?
Right. So I think you would need to have the cycle information, like you're saying, the pressure ratios, the temperature ratios. I think you would have to have a reasonable idea of what your geometry is going to look like. So in this work, we started with the 3-stream nozzle. So we at least know what that kind of very basic nozzle shape looks like, right? We have something round, the multiple streams. So I think they would need to know that. And then I think a user would need to know what kind of parameters they want to tweak on there and how they would go about doing that. So, you know, for example, in this work, we just looked at the 3rd stream, but there's a lot of other parameters you could tune with this as well. And then I think what we found is that some of those closure parameters, the model wasn't super sensitive to that. So I think as long as you have, you know, a round nozzle and, you know, those parameters probably would work well. If it was a square type nozzle, then we might have to update some of those parameters. But I think if you have a baseline geometry and some operating conditions, that's more or less what you would need.
Okay. Well, thank you. There's a couple questions. We'll save those for answering asynchronously.
Excellent.
Yep.
Thank you, Chris.
Thank you.
Our next speaker is another SBIR activity, Enrico Fabiano from Scientific Simulations. I think Enrico's online, if you could confirm that. And this will be an adjoint-based optimization of nozzle designs for reduced supersonic jet noise. So.
And I'm online.
Great.
I'm just trying to share my presentation. Give me one
well,
second.
Good news is we hear you and we see your screen.
Good.
So we're getting close.
Second, otherwise, I'm going to ask you to present it for me.
We can do that as well.
Yeah, okay. This is fine.
So Raj, yeah, that's working. Let's give Enrico another couple of seconds and getting closer.
Is the presentation up now?
We're seeing your view, not the presentation view. We're seeing the thumbnails and the top banner.
Yes, we want to. I guess we want to try, if you guys can.
Okay, yeah, Raj will present and then you can just verbally tell him when to move on. Thank you.
Thank you. All right, I'm just going to present my perfect. Hello, everyone. Thanks for being here today. My name is Enrico Fabiano, and I want to talk to you about what my coworkers and I have been working on in the past few years as part of a NASA SBIR project that focused on the development of an adjoint-based sensitivity analysis capability for reduced supersonic jet noise. Next slides, please. Just a brief outline of the presentation. I'm going to give you a quick introduction and then state the SBIR objectives. And then from there, we'll move on to describe the hybrid CFD-CAA analysis and adjoint sensitivity approach that we developed in this work. Then we're going to take the adjoint sensitivity approach and we're going to use it to perform some design optimizations. And then from there, we'll draw conclusions and highlight possible future work. Next slide, please. So the design of the next generation of commercial supersonic aircraft is an intrinsically multidisciplinary design optimization problem. Today we want to focus on on air acoustics. The commercial supersonic fleet will have to comply with increasingly stringent noise regulations, community noise regulations, and today we want to tackle the issue of jet noise. What we really want to do is enable adjoint-based nozzle shape optimization with the goal of minimizing noise with possibly no performance penalty. And to be able to do that, we need to develop an air acoustic adjoint-based optimization capability, which is essentially the objective of the SBIR. Next slide, please. So what we want to do is basically leverage or use NASA knowledge, software, tools in the field of jet noise to develop a multidisciplinary adjoint-based sensitivity analysis that enables the next generation of commercial supersonic nozzles. Essentially, we want to be able to compute the CFD solution around a nozzle using a RAN CFD solver like NSC3D and Fun3D. And then we want to take this solution, give it to the Geno 2.5D jet noise code that has been developed at NASA Glenn. And the Geno will be able to compute the far-field noise spectra at the acoustic observers. And then we want to take these noise spectra and give them to an OP2 to compute objective functions, acoustic objective functions, like, for example, PNL, PNLT, or maybe PNL in the future. And we'll target, and our optimizations will target these objective function computed by an OP2. But of course, we also want to be, since we want to enable adjoint-based design optimization, we also want to be able to compute the sensitivity with respect to the objective function computed by an OP2 with respect to the design variables that we define in our CFD model. And that's why we need to develop this adjoint-based sensitivity analysis capability that is the focus of this SBIR. Next slide, please. With that, I'll dive into the details of the hybrid CFD CAA analysis and adjoint sensitivity approach that we developed, and I'll start with the aerodynamic analysis. Next slide, please. Which is based on the NSC3D, 3D unstructured finite volume RAN solver. The solver is second order accurate in space. We will be using a 2-equation K omega turbulence model. The solver is enhanced with its exact discrete tangent and adjoint linearization, and it also has a deformant mesh capability that we're going to use to propagate the displacement of the surface mesh to the interior mesh, to the volume mesh. And this displacement will come from design changes that the optimization algorithm will propose as part of the optimization process. Next slide, please. Once we compute basically the CFD solution around the nozzle, then we'll pass it to our acoustic analysis or to our acoustic approach, which is based on the Geno 2.5D code as I mentioned earlier. Next slide, please. Geno 2.5D is a jet noise code that has been developed at NASA Glenn, and is based it's capable of predicting far-field noise spectra using Lively's acoustic analogy. Essentially, Geno expects a structure grid and a steady RAN solution on that structure grid, and from this RAN solution, it will be able to compute the noise spectra for both hot and cold jets. And it also perform the noise spectra will be computed both at the for observer at right angles from the nozzle axis, or for more general observer locations, like for observer at 60 degrees or 150 degrees, for example, from the nozzle axis. However, in this case, in the general observer case, Geno computes the propagation grim function via the integration of a system of ODEs, and the numerical integration of the system of ODEs is performed using an adaptive algorithm that is a computational intensive step in the jet noise process. And so we'll show what we did to mitigate this issue. Finally, we developed the coupling between Geno 2.5D and an OP2 to essentially enable the prediction or the computation of certification acoustic metrics, like, for example, PNL, PNLT, or maybe EPNL. Next slide, please. This is the acoustic problem that we're basically going to look at for the remaining of the presentation. The nozzle we'll be working on is the SMC006 nozzle that is represented by its unstructured surface mesh in red in the picture. And then we also showing here the Geno structure grid that extends from the nozzle exit all the way 40 diameters downstream of the nozzle exit. And in the radial direction, the Geno structure grid extends for about two diameters. The flow conditions correspond to set point 7 in the Tana matrix. Next slide, please. And are briefly summarized here here in the slide. For those of you not familiar with the SMC006 nozzle, the nozzle is a 2-inch round nozzle with 6 triangular chevrons. We built an unstructured grid around it. The grid consists of about 2.3 million grid nodes, and the geometry is being parameterized with the 3 design variables: chevron penetration, chevron twist, and nozzle length. And I'm showing these design variables in the next slide. Next slide, please. From left to right: chevron penetration, chevron twist, and then chevron length. Next slide, please. So the first thing after computing the solution, the CFD solution around the nozzle, was to basically perform a validation of the computed aerodynamic near field. And we're doing this here by comparing contour of total pressure computed by NEC3D with available experimental data from an experimental campaign that was performed, I believe, at NASA Glenn a few years back. As you can see, there's good qualitative agreement between the computed and measured contours. So we're kind of confident that we're reasonably confident that we can predict the aerodynamic near field accurately. And so we can take then this aerodynamic near field and give it to Gino to essentially perform jet noise prediction at far field observers. Next slide, please. However, before we can start using Gino to perform jet noise prediction, we need to find a way to couple NEC3D, the unstructured NEC3D flow solver with the let's say structured Gino code. Structure in the sense that Gino relies on a structured grid. And next slide, please. So essentially, the problem here is that of interpolating the unstructured CFD solution in NEC3D onto the Gino structure grid. And to do this, we decided to follow an overset approach, and we're going to use the Tioga overset domain connectivity algorithm. And essentially, this will allow us to couple in memory, couple the NEC3D flow solver with the Gino 2.5D jet noise code. Next slide, please. After we couple the flow solver with Gino, we decided we needed to perform a validation of our jet noise prediction, and then that's basically what I'm showing here. I'm showing the noise spectra for a 90-degree observer as computed by Gino with our CFD solution, and also as measuring the experiment from the same experimental campaign that I mentioned earlier. As you can see, there's good agreement between computed and experimental spectra, and so this gives us confidence that basically our analysis approach that we developed, so the coupling of NEC3D with Gino, is accurate, and so we can start developing the edge linearization of this system, of this coupled system, and then start performing some optimization. Next slide, please. So with that, I'll briefly dive into the details of the edge linearization. Next slide, please. I won't bother you too much with the details of how we develop the edge linearization. I have backup slides if we want to talk about it. But basically, we follow an approach where we first develop the tangent linearization, and we verify this implementation with respect to the complex step method or the finite difference method. Once we're satisfied with this verification step, then we move on to the edge linearization, to implementing the edge linearization, and which we verify by the duality relation with the implemented tangent linearization. And once we're satisfied with our implementation of the edge linearization, then we essentially move on and start performing optimizations. For the case of Gino, we developed the linearization of the OSPL objective for both hot and cold jets. We also developed the edge linearization for the thrust objective that is computed by Gino at the nozzle exit plane. And then finally, we developed the linearization of the Gino and Op2 coupling as well. Just wanted to mention here that the linearization that we developed for Gino is valid for both the 90-degree observer case and the general observer case. So for observer that are at general angles from the nozzle axis, so for example 60 degrees or 150 degrees, and in this case we also linearize the adaptive ODE integration algorithm that is used to compute the propagation Grimm function, and this is another and this is a computational intensive step of the sensitivity analysis process. And so we'll see what we did to mitigate this issue. Next slide, please. I'll start with just briefly showing the verification of the implemented sensitivities for a 90-degree observer case. Here I'm showing I'm comparing basically the sensitivities computed with the complex step method, with the tangent linearization, and with the implemented adjoint linearization for OASPL as computed by Gino. The sensitivity is with respect to the chevron penetration design variable, and we're checking basically the sensitivities of both cold and hot jets. And as you can see, there's excellent agreement between all the implemented sensitivities. Additionally, I'm also showing the verification of our sensitivity of the implemented sensitivities for the thrust objective computed by Gino at the nozzle exit. And again, there's excellent agreement between all the implemented sensitivities. So we're confident that our linearization, the implemented linearization is accurate, and we can use it for design optimization purposes. Next slide, please. As I mentioned, we also developed the adjoint linearization for the NSC3D, Gino, and OP2 in-memory coupling. So the coupling of NSC3D, Gino, and OP2 allows us to compute PNL, PNLT, and in the future also other certification noise metrics. And I'm showing an example of this NSC3D, Gino, and OP2 coupling in the table on the bottom left, where I'm showing the computation of PNL and PNLT for the SMC006 nozzle and an observer at 90 degrees from the nozzle axis. But as I mentioned, we also developed the adjoint linearization for the coupling, for the Gino and OP2 coupling, and that's what I'm showing on the table on the right, where I'm showing the sensitivity of PNL with respect to the chevron penetration design variable for a 90-degree observer, and I'm comparing the implemented tangent and adjoint linearization with respect to the finite difference method. Again, there's excellent agreement between all the implemented sensitivities, and so we're confident that we can use the adjoint linearization to perform general noise prediction, gradient-based optimization. Next slide, please. Here I'm showing the verification of the sensitivity for the general observer case. This is a reasonably computationally expensive gen noise prediction and sensitivity analysis, because we're performing the integration of the system of ODEs to compute the propagation green function, and also we're performing the linearization of the system of ODEs to compute the sensitivity of the propagation green function. And we have excellent agreement between the implemented tangent and adjoint linearization. Unfortunately, the agreement with the finite difference method is not as good as it was for the 90-degree observer, but we believe that it's acceptable for MDO purposes, and we'll see that in fact we were able to use this linearization for a design optimization. Future work will focus on improving the accuracy of the implemented linearization and the agreement with the finite difference method. Next slide, please. Here I'm showing basically that we developed a MPI parallel version of Gino, and this is essential. This was basically developed with the general observer case in mind. As I mentioned, the integration of the propagation green function and the associated adjoint linearization is a computational intensive step of the jet noise prediction process. For example, a jet noise prediction for an observer at 150 degrees for the serial version of Gino would take about 45 minutes, but with the MPI parallelization, we were able to reduce the computational time of the jet noise prediction to about 4 minutes. And this is essential for design. And these results carry for the adjoint linearization as well. And this is essential for design optimization. The MPI parallelization is essential for efficient design optimization, as we'll see later. Next slide, please. Finally, before we can move on and start performing the optimization, we just needed to implement the linearization of the ATWG overset domain connectivity algorithm. And this is going to be used to exchange sensitivity information from NSC3D to Gino, or actually from Gino to NSC3D. And I'm showing here the verification of the duality, the verification of the implemented tangent and adjoint linearization via the duality relationship. Next slide, please. So with that, I think we have all the pieces in place, and we can start performing some optimizations. Next slide, please. Next slide, please. Can you go back to one slide, please? Thank you. The problem, as mentioned at the beginning, the problem is that we're gonna work on today is basically that of minimizing the noise of the SMC006 nozzle with possibly no performance penalty. We're gonna look at basically two different optimization problems. In one case, we're gonna try to perform just an acoustic optimization. We're gonna try to minimize an acoustic objective function that will be either OSPL as computed by Geno or PNL as computed by an OP2. And the optimization will be performed with respect of the 3 design variables that we defined earlier. We will also try to perform an acoustic optimization where we'll basically we'll try to minimize noise, but we'll also enforce an aerodynamic constraint. We will essentially require that the thrust of the optimized nozzle, as computed by Geno, is the same or as close as possible to the thrust of the baseline nozzle, again as computed by Geno. This aerodynamic constraint or this propulsive constraint will be enforced using a penalty function approach. And I'm showing essentially the final objective function in the equation on the right. The minimization will also be performed with respect to the 3 design variables that we defined earlier. We're going to perform optimization for 2 different observer locations, a 90-degree observer and a 60-degree observer. For the 90-degree observer optimization, we will be performing 2 acoustic optimization and an OSPL-based optimization where OSPL is computed by Geno, and a PNL-based optimization where an OP2 is computed by Geno. We'll also be performing an acoustic optimization where, as I mentioned earlier, we'll be combining basically the OSPL objective with the thrust constraint. For the 60-degree observer, we'll be performing an acoustic optimization, online acoustic optimization, where we'll try to target we will try to minimize OSPL as computed by Geno. And for all these optimization, we will use a gradient-based design optimization algorithm, an unconstrained gradient-based design optimization algorithm, where the gradient is computed using the adjoint-based sensitivity analysis that we developed in this work. For all the optimization, 1 design cycle will correspond to 1 flow solution and 1 adjoint solution. For the computational cost of 1 design cycle correspond to is about 40 to 45 minutes on 144 cores, and depending on the observer location, 90-degree versus 60-degree observer. Next slide, please. So now diving into the results of the optimizations, this is the OSPL-based optimization for a 90-degree observer. I'm showing convergence of the optimization on the left, and on the right, there's basically I'm comparing the baseline nozzle shape and the optimized nozzle shape in green. We managed to achieve about approximately 1 dB reduction in OSPL, but this comes at this is achieved by increasing chevron penetration, while the other 2 design variables played a more marginal role in the design optimization process. Next slide, please. Here, I'm basically comparing the noise spectra at the observer for the baseline and the optimized nozzles. And on the right, I'm showing basically the table with the optimization, with the results of the optimization. You can see that we successfully reduced noise by about 1 dB. But this noise reduction came with a significant with a degradation of the performance of the nozzle, of the propulsive performance of the nozzle, and so we'll try to address this in a subsequent optimization. Next slide, please. This is the optimization that targeted the PNL objective as computed by an OP2. And the acoustic observer is at right angle from the nozzle axis. This essentially is the optimization that uses the adjoint-based sensitivity analysis approach that we developed in this project. So the combination of the adjoint in an OP2, in Geno, and in NSE3D. On the left, I'm showing convergence of the optimization, while on the right, I'm comparing the shapes of the baseline and optimized nozzle. The baseline nozzle is in blue. The optimized nozzle is purple. We achieve approximately a 2 dB reduction in PNL at the observer, and the reduction is achieved by increasing chevron penetration, while the other 2 design variables play a more marginal role. Next slide, please. And here, similar to what I did before, I'm comparing the baseline spectrum with the optimized spectrum at the observer. And the table on the right shows the results of the optimization, where basically I'm showing the approximately 2 dB reduction in PNL, but again, at the expense of the propulsive performance of the nozzle. Next slide, please. We decided, after completing these two optimizations, we decided to compare the two designs, the two nozzle designs that we ended up with, and that's what I'm showing here. The purple nozzle is the PNL optimization, while the green nozzle is the OSPL optimization. And as you can see, the two optimization results in very similar nozzle. Next slide, please. As confirmed by so a similar nozzle as confirmed by the two noise spectra, by a comparison of the noise spectra. Next slide, please. So just to summarize, we performed two different optimization: OSPL based with Geno and PNL based with Geno and an OP2. Both result in a similar nozzle. Both nozzles suffered a significant performance penalty. So what we're going to try to do now is keep the noise reduction, but we'll try to also enforce a aerodynamic constraint to perform a propulsive constraint in the hope of keeping the thrust of the baseline nozzle for the optimized nozzle as well. And I'm showing the results of the convergence of the optimization on the left, while on the right I'm showing basically the baseline nozzle shape and the optimized nozzle shape. Again, we achieve a approximately half a dB reduction in OSPL. And the noise reduction is achieved by increasing chevron penetration, while the other two design variables play a more marginal role in the optimization. Next slide, please. Here on the left, I'm showing a comparison between the baseline noise spectrum and the OSPL-based noise spectra in green, and then you can see that the noise spectra for the nozzle design in this optimization and this air acoustic optimization is a compromise between the noise generated by the baseline nozzle and the noise reduction of the OSPL-based optimization. But as the table on the right shows, we achieve essentially half a dB reduction in OSPL, but we don't suffer such a severe performance penalty as we suffer for the OSPL-based optimization, and this is due to enforcing the thrust constraint using the penalty function approach. Next slide, please. This is the final optimization that we performed. This is the optimization of the target's OSPL as computed by Geno for a 60-degree observer. And I'm showing convergence of the optimization on the left, showing that essentially, even if our sensitivities are not perfect, they're still useful for design optimization purposes. And on the right, I'm showing the baseline in blue and optimized nozzle geometry in black. And for this optimization, we achieve a 1 dB reduction in OSPL for the observer at 60 degrees. This noise reduction is achieved by increasing chevron penetration again, while the two design variables continue to play a marginal role in the optimization. Next slide, please. Here on the left, I'm showing a comparison between the baseline and optimized, between the noise spectra for the baseline and optimized nozzle. And on the right, I'm showing the result of the optimization, a table with the result of the optimization. As you can see, there's 1 dB reduction in OSPL. And this comes with the severe performance penalty consequence of not enforcing the propulsive constraint, the thrust constraint using the penalty function approach. Next slide, please. We finally wanted to compare basically the results of the 90-degree the designs of the 90-degree optimization with the design of the 60-degree optimization. And what we notice is that despite the different observer location, the optimizations results in very similar nozzles. And this, together with everything else that we've seen during while performing our optimization, lead us to believe that we have a limited design space that is mostly dominated by chevron penetration, with the other two design variables that are not playing a significant role in the optimization process. Next slide, please. But this essentially summarizes our work so far, and so with this we'll draw some conclusions, and then I'll highlight future work that is currently underway. Next slide, please. So we basically succeeded in developing an adjoint-based sensitivity analysis capability for jet noise based on the NSE3D flow solver and on the Geno jet noise code and the NOP2 software from NASA. we use this adjoint-based sensitivity analysis capability to minimize the noise of the SMC006 nozzle. Unfortunately, we experienced limited design space in our optimizations. Not shown here, but we also worked on coupling Fun3D with Geno. Next slide, please. In the future, we intend to try to improve the accuracy of the sensitivity for the general observer case, but we also want to focus on more advanced optimizations, like optimization that would target multi-stream nozzles. I'm showing a solution, a preliminary solution of the computed with NSE3D around the multi-stream nozzle geometry that we're currently working on. With that, I will take any question. I'll thank you for your attention, and I will take any question that you might have.
Thank you very much.
Yes, thanks, Enrico. I have a question. So if the design doesn't stray far from SMC 006, if you started with a geometry that was close, would you converge to SMC 006 with your method?
Yes, I believe it would. In fact, it was trying to even exceed what the SMC 006 nozzle was doing, and actually increase the chevron penetration farther. So I believe that yes, we would be able to converge to the baseline nozzle.
Okay, there's a question. Have you compared the RANS flow fields of the optimized nozzles to the baseline design?
I believe we have at some point. I think that we're seeing improved mixing, if I don't remember, for the optimized compared to the baseline. If I don't remember, if I remember correctly.
Okay, and there's one more question, which is kind of complicated, so I'll just summarize it. So it says that the noise reduction that you're finding of approximately 1 decibel is less than the difference between the model and experiment, which was around 2 to 3 decibels. Do you have a comment about that?
Yes, we could have let it go further by increasing chevron penetration further, but basically what was going to happen was that we would have suffered an even more severe performance degradation in terms of thrust. Our design space was, or the design variables that we chose were useful to prove that our adjoint-based sensitivity analysis capability is working and is actually capturing the correct design trends. But for more realistic optimizations, the design space will have to be parameterized differently, I believe.
You have very limited control authority on getting what you want to achieve. Yeah.
Yes, exactly. So we need to do a better job there. So
yeah.
Okay, well, I recommend we forward the rest of that question and you can answer it.
Yes,
in long form. Okay. Bye.
Yeah. Okay, at this point, I want to thank all the speakers who were with us this morning, if they're still with us, and thank you to the audience. We're now taking our East Coast, West Coast lunch break. I guess this is somewhere in the late afternoon for Europe. We will reconvene at 1:15. The first speaker in the afternoon is Muni Majiji, who used to be a senior acoustician at GE and is now with the FAA. So everyone, enjoy your hour break, and we'll see you again at 1:15. Thank you.
Right. Good afternoon, everyone. I hope everyone had a good lunch and is looking forward to an afternoon of a couple of talks here regarding more jet technologies. It's a relatively quick, will be done by around 4 p.m. Eastern Time. First up, we have Muni Majigi, who will be talking about some of the role and challenges that the FAA and we have regarding sustainability. So without further ado, I will pass it off to Muni. Thank you very much.
Thank you, Jordan. Good afternoon. My name is Muni Majigi. I serve as Senior Technical Advisor in the Noise Division of the Office of Environment and Energy of FAA. And on behalf of the AE team, I really appreciate this opportunity to present our views on sustainability challenge that's facing the aviation sector, and we as a team can address this challenge. Next chart, please. A brief outline of my presentation. First is the motivation. Why do we need to do this? And what are some potential approaches? And what's FAA doing on these? And the close partnership between NASA and FAA, and then some summary thoughts. Okay. Next chart, please. The sustainability imperative. I'm sure you've been reading about this a lot in the press lately. And before going to the details, I wanted to summarize what this imperative is that aviation has to face. The global situation has been rapidly changing. The aviation industry has been significantly impacted, as you know, from several environmental pressures, climate, noise, local air quality around the airports, the economic pressures, COVID-19 and other events. So the sustainability has become a key to survive and thrive. And we feel that we have the ability to face these challenges head on and seek out opportunities among these challenges and still maintain or enhance our leadership position. We feel that a challenge can also become an opportunity, but to make that happen, the business as usual kind of approach most likely will not succeed. So we need to look for some creative solutions at all levels, not just at some fields or other fields. So to address this sustainability, understanding of the interdependence between competing factors is essential. So to some extent, as I listened to the morning talks, a lot of the subject matter experts have gone into a lot of technical details, and the subject matter experts also will have to serve as generalists in some sense to understand the connectivity between noise, fuel burn, climate, etc. Once one has that understanding, we think we'll be, as a team, develop some creative solutions. Next chart, please. We go to the next chart. Yeah, thank you. Recently, that's on the September 9th, the Biden administration conducted a virtual event dedicated to sustainable aviation. And this fact sheet on the right side is available on the web. You can download it and read it in detail. Basically, on the 9th of September, leaders from the government and the industry announced some specific actions to produce 3 billion gallons of sustainable fuel, reduce the aviation emissions by 20%, and also develop good paying union jobs. So there are a lot of details in this fact sheet, but the key items that pertain to what we are doing are on the left side. They are basically increasing the R&D activities to demonstrate new technologies to achieve at least 30% improvement in aircraft fuel efficiency. And NASA has launched a Sustainable Flight National Partnership, SFNP. It's kind of complicated acronym. Is to collaborate with the FAA and the industry to accelerate the maturation of aircraft and engine technologies to really jumpstart and achieve step change reduction in fuel burn and CO2 emissions. At the same time, as you heard in the morning, Levent and Arthur talked about the Clean 3. FAA has awarded more than $100 million for aircraft engine companies to develop and demonstrate aircraft technologies that reduce fuel use, emissions, and noise. So the Biden administration's overall goal has been to achieve a fully zero carbon aviation sector by 2050. And that is certainly a very challenging goal. Thank you. Next chart, please. So what are some actions the US government is taking to reduce this aviation emissions? These are the 4 specific pillars, as we call them. On the leftmost is the technology element, where we want to develop more fuel efficient aircraft and engine technologies through public-private partnerships. And then followed by the sustainable fuels, which are very key to meet the aggressive CO2 reduction goals, and operational aspects to make sure we modernize and run the NAS system very efficiently to minimize the fuel burn and CO2 emissions. And lastly, but not least, policy measures and certain market-based approaches to get to the carbon neutral goal. So one thing to note is this carbon neutral growth by 2050 is a very challenging problem, and it is our problem. So all the combinations of these 4 items, technology, sustainable fuels, operations, policy measures, are necessary to achieve such an ambitious goal. And although some specific fuel burn improvements may provide large fuel burn compared to current technologies, the penetration of such technologies into the fleet takes time. So larger fuel burn savings and quicker fleet penetration will hasten the reduction of CO2 emissions, and that could alleviate some requirements of the operations, for example. Okay, so next chart, please. This one kind of sets the stage in terms of what's happening in the global environment and economic arena. On the left side is the so-called economic perspective, which shows the airline industry has been hard hit by the COVID-19. The global competition is growing, and particularly in the US, the limited industry funding for R&D investments. The middle chart shows the CO2 emissions with year. If we don't do anything, it shows how the CO2 reductions, CO2 emissions will continue to climb. And that's a huge problem. To achieve the carbon neutral growth, you have to bend the curve downwards rather than the way it's going. So that's where this technology, infrastructure improvements, market-based measures, etc., will play a key role. And the last chart is a national noise curve based on the recent neighborhood environmental survey FAA conducted, which shows the DNL on the x-axis and % people annoyed. And this one basically shows a lot more people are getting annoyed compared to what has been historically used in the US. So this will also put pressure. So as we see, there's an economic pressure, there's an environmental pressure in terms of CO2, and then in terms of the local noise issues, people are getting more and more annoyed with the airplane noise. And this is reflective of not just in the US, but in other countries as well. So we need to be aware of these pressures. So let's see what we can do about this. Can you go to the next chart, please? Yeah, okay. This chart shows how the noise and CO2 regulations have been evolving. On the left side shows the CO2 metric value as a function of airplane takeoff mass. That's the new ICAO regulations that has been enacted. And it also, the blue line on the left side shows the current not to exceed CO2 metric value based on the airplane max takeoff mass. And then you see the red line, that's the Clean 3 phase goal that Levent showed this morning. And the other two represent CAPE independent expert review panels. One is a midterm and the other one is a long-term goals. So what we see is there is a regulatory requirement to certify the airplane, but there are also goals that are more aspirational to help achieve the lower carbon emissions. On the right side, this is a chart I'm sure many of you are familiar with. This is the noise rules, how they have become more stringent over the years. And the latest one is the so-called Chapter 14 in the ICAO terminology, or what's called a Stage 5 in the US. The blue dots on the right side show some of the airplanes that have been certified related to the noise rules and the year of certification. And so I said before, in order to achieve sustainable aviation sector, we will need to go beyond these current CO2 standards and national global goals. So to address the community noise concerns, we need to achieve further reductions in noise source, because that's probably the most effective means among the so-called balanced approach to reduce the community noise exposure. So, okay, next chart, please. Yeah, this one in the morning, somebody talked about the noise around the airports. What you see is a picture of the Boston Logan Airport on the lower right side, and the red bands show the typical departure profiles, and the green ones show the arrival patterns. And also you will see there's a 65 DNL contour on the overlaid over the runways. And each blue dot represents a noise complaint received from the neighborhood. As you can see, many noise complaints are from areas outside the 65 DNL contour, which has been traditionally used as the annoyance metric. So as we can see, as the number of flights have increased and the air system has become more efficient by having these tight corridors, the number of people getting annoyed is also increasing. And the upper right picture shows with time how the operations at the Boston airport have increased, almost starting from 200,000, getting close to 400,000 by 2018. So here is one example where noise regulations by themselves may not be sufficient. We'll have to address these annoyance concerns from the population. Okay. Next chart, please. So that kind of sets the stage in terms of the noise issues and the problems we're facing. And so US has been investing in aircraft technology for a long time. And such investment has been very important to promote a healthy aviation sector. Such investment is all the more critical now due to a confluence of multiple factors such as we talked about the COVID-19 impact on the aviation industry, increased pressure to reduce the aviation's contribution towards global climate, as well as community noise and local air quality issues around the airports. The top chart shows the fuel efficiency improvement in terms of passenger miles per gallon over the past 30 years. So it shows almost a 70% increase in fuel efficiency over the 30 years, which translates to like 1.8% improvement per year compounded. And the bottom chart shows almost 94% reduction in the US population exposed to 65 DNL since 1975, whereas the number of people flying has increased by 350% at the same time. So that is, the population within the 65 DNL has decreased by like 1.5% per year, whereas the traffic has increased by almost 3.4% per year. People, I mean. So remarkable as these achievements look and are, we can't rest on these laurels because sustainability pressures were talked about before, and we need to make further significant reductions in fuel burn and noise, and that will require investing in high risk and high payoff technologies. And when the risks are high and the payoffs may be high, the industry typically is shy of taking such risks. In such situations, the US government's resources can help mitigate the technological risk and incentivize the aviation manufacturers through a public-private partnership to develop cleaner and quieter technology. And Clean is one such vehicle. And NASA's many research programs are also public-private partnerships. So those are the vehicles we see as ways to incentivize to take risks and develop more high risk, high payoff technologies. Okay. Go to the next chart, please. So now that we talked about the motivation, what are the potential approaches? So next chart. So here is a chart. This probably you have seen this type of a chart, which shows how the turbofan technologies have evolved over the years. So on the left side plot shows the fan size increasing to the right, which means to produce the same thrust, you get to larger fan by lowering the fan pressure ratios and resulting higher bypass ratios. So you want to push more mass flow to make the same thrust. And when you do that, what happens is shown on the y-axis. The blue is the noise and the red is the fuel burn. And as we've seen in the past, as you go from bypass ratio like 5 to 9 to 12, the noise has come down significantly. And it's kind of shows a little bit of a plateau that it's becoming difficult to get more noise reduction as you keep increasing the bypass ratio. And then on the red lines are the ones that show the fuel burn. And the fuel burn certainly goes down as you reduce the fan pressure ratio because the propulsive efficiency increases. But it seems to bottom out because the nacelle gets bigger, draggier, heavier, and there's an optimum in terms of the fuel burn versus the fan pressure ratio or the bypass ratio. And if you can reduce the weight of the nacelle and the drag of the nacelle, the bucket will move to the right. So that's the way to get to a higher bypass ratio, which is pretty good in terms of getting higher propulsive efficiency due to reduced fan pressure ratio. And also the noise keeps coming down. So we had to see how to lower the noise steeper than the way it is so far. And the right side, you see a picture of an airplane. As you keep increasing the fan diameter for lower fan pressure ratios, you start seeing the ground clearance issues. And the engine gets stuck more and more under the wing. and so on. So it becomes installation becomes difficult for some of the standard under the wing installations. So we had to kind of creatively think, how do we accommodate lower fan pressure ratio cycles and with minimum installation penalties? Okay. So let's go to the next chart. Yeah, these are some of the propulsion system design traits that are typically done. On the left side, you see a bunch of blue circles or blue ellipses, and the green ones are the blue ellipses are the design selections, what you can choose or what you want to go after, and the resulting benefits are shown in the green, and the penalties are shown on the yellow. For example, if you take the increased bypass ratio as 1. Increased bypass ratio reduces the engine specific fuel consumption and the CO2 emissions. It reduces noise, but on the penalty side increases the fan diameter and the engine weight. And if you go to maybe take a higher component efficiency, the top blue ellipse, that always helps in terms of reduced specific fuel consumption and CO2 emissions, but the cost will go up. So, and things like that. So there are lots of these trait parameters that engine or OEM will evaluate to balance the benefits and the penalties. And on the right side, you will see a cycle trait, which shows the interplay between the fuel burn on the y-axis, LTO NOx, that's the engine NOx emissions on the x-axis. And then there are lines of constant fan pressure ratios and lines of constant engine overall pressure ratios. So this one is called a carpet plot. It basically shows if you want to get to a minimum fuel burn, if get to fuel burn, that's a red dot that's at the bottom, where is LTO NOx shown as 100%. And if you were to go up, if you want to reduce low LTO NOx, you would go to the left of that, and that will cause increase in fuel burn. Typically, the fuel burn and the noise go hand in hand up to a point like we talked about. So these kinds of cycle and design parameter selection shows what kind of penalties and benefits are there and where could the optimum system be there. So these have been done in the past and will continue to be done, but this is not enough. So what do we go, where do we go next? So if you go to the next chart, this one shows for a given selection of a design parameters, say fan diameter or cycle pressure ratio or T41, whatever, can you bring in noise technology and fuel burn technologies into the design so that you can push the fuel burn and the noise lower. So this chart was taken from a CAPE independent expert review panel. It's kind of small, but the idea is on the left side, the focus is fuel burn reduction. On the right side is the noise reduction. And then there's something called as a domain, means on the fuel burn, let's see the propulsion, the structures and aerodynamics, etc. Those are the major disciplines, and things under them show the various approaches that can be used or technologies that can be used to influence fuel burn. On the noise side, it's a very similar thing. It's broken into engine, airframe, nacelles, etc. And by components, what kind of a technologies one can go after to reduce them. And when you look at these things, there are some technologies which appear on both sides. And so there is interdependency between reducing the fuel burn and reducing the noise. And there are some technologies which will help both, which will reduce the fuel burn and the noise. And there are some where you will suffer a fuel burn penalty for improving the noise. And the ones we had to go after are those win-win. You may say, are there any? And there are many such win-win technologies. One is lighter weight materials. If you have lighter weight materials, airplane will weigh less, you will burn less fuel, you'll make less noise. And then other one is if you were to go with a higher aspect ratio wing. Higher aspect ratio wing provides better lift to drag ratio, which is good for performance and fuel burn, and higher aspect ratio wing gives higher lift to drag, which also helps the airplane to achieve higher altitude over microphones. Oh, no. So, those are the kinds of win-win technologies that we need to go after to reduce fuel burn and noise. And when nothing else is there, then you want to go after trades. For example, Chevron is one such. If there's nothing else left there, Chevron typically gives you noise reduction, but at some fuel burn penalty. Those are not highly preferred, but they may be the best you could do in certain situations. Okay. Let's go to the next chart, please. So this one is an outcome of the technology selection that I showed the previous slide. So what this one shows is on the y-axis is cumulative noise levels, and on the x-axis it shows the fuel burn in kilograms per allowable ton kilometers. And what you see is the Pareto set of charts, curves, that show how the trade happens for given technology assumptions. The topmost on the rightmost corner is a current technology reference airplane, and it shows green and red dots, which show how the bucket or where the sweet point could be for a selection of the minimum noise and minimum fuel burn impact. The green dot reflects such a point. And then if you were to bring in different technology assumptions, that the top three curves, the topmost on the right side, they reflect the 2027 kind of technology, and the most aggressive one are the ones that show the lowest cumulative noise and the lowest fuel burn. Once you make those technology selections, you do your design trade studies to pick the point of the interest where you balance the noise and fuel burn. And the more the aggressive the technologies, the less confidence one would have and probably more benefit. So this is the basically high risk, high payoff technologies. So these are the kind of things one needs to keep in mind as you look for a win-win situations. Okay, next chart, please. So we talked about the motivation, talked about the potential approaches, and then briefly talk about what FAA is doing or has done. Okay, next chart. FAA has taken a comprehensive approach to address environmental challenges. We know one thing will not fix all our problems, so we had to look at a broad range of stakeholders to understand the issues and develop the solutions. And then we need to place more focus on how do we overcome noise and emission challenges and continue to seek partnerships. So on the right side, you see the pictures. The top one, which shows the sustainable alternate fuels being delivered on airplane. Below that is how do you operationally improve the situation to reduce the noise and fuel burn. And the two below that show advanced technology airplane like 87 and probably a new configuration such as the D8. So we need to employ all these tool sets that are under our control, so to speak, to go after noise and the fuel burn. Okay. Next chart, please. So FAA at the Office of Environment Energy has employed a three-phase strategy. The three phases are shown in the white boxes. One is advanced understanding of the noise emissions and their impacts. First, understand that. Then develop and employ analysis tools to help decision making. And then the third one, probably the most important one as we are concerned in terms of technology, is to develop innovative solutions to reduce noise and emissions. And that's the develop innovative solutions to reduce noise and emissions. Under that, you see three lines. One is the aircraft engine technology, sustainable alternate fuels, and optimize operations and procedures. So those are this is our overall strategy that has helped us over the years. And we think when we continue to work these problems, this kind of a strategy will continue to keep our focus. Okay. Next shot, please. Yeah, we talked this morning, Levent and Arthur talked about the clean in quite a bit of detail. I don't need to go over that. And also there is asset COE, that is the similar but FAA partnership, but with academia, where there's again 100% in kind cost share. Here, the focus is on a broad range of innovation solutions, technology, fuels, ops, etc. And these tend to be, it could be any technology at any TRL, but with understanding that FAA has a focus on applied R&D, and universities use this knowledge gain to improve the knowledge broadly. But there are opportunities to examine technology under NDAs also. And as far as clean is concerned, the basic focus is to mature the technologies from a TRL 3 to 5 to TRL 5 to 7. Okay. Next shot, please. Yeah, I don't need to go through this. It shows the three phases of phase 1, phase 2, phase 3 that Levent and Arthur explained, and what the time frame is, what the budget has been, and what the goals are, etc. We had a very good review with them today, and we're excited about the Clean 3 contract award announcements and look forward to those cleaner and quieter technology development for future products. Okay. Next shot, please. So then there was a question, okay, with all this clean activities done, what have we achieved? This also was discussed there in the morning presentation. It shows the fuel burn benefits of the Clean 1 and Clean 2. And in terms of the fairly large fuel burn reductions, but as we can see, those reductions build up over time, and it takes into account how the fleet evolves with that incorporates those advanced technologies. Those things do take time. A similar exercise is going to be done for the Clean 2 and the noise, but Clean 1 showed about 14% decrease in the land area for the DNL 65 dB contours. Next shot, please. So I wanted to spend a little bit of time on this noise reduction technology. It's becoming with this higher bypass ratio engines and the lower fan pressure ratio. We're getting higher propulsive efficiencies, of course, and when you couple it with higher core pressure ratio, we get higher thermal efficiency. So that motivation to go there is going to be there because you get both higher propulsive and thermodynamic efficiency, which helps fuel burn. But when you do that, the noise breakdown or the component breakdown among the engine and airframe keeps changing. When you go for the lower fan pressure ratio, this chart basically shows it's an average of the takeoff and approach are the two major columns there. And on the left side, you see the takeoff, which is an average of sideline and flyover. It shows the three bars, the airframe, the engine, and the total, and then a further breakdown of the engine components, jet, turbine, combustion, forward fan noise, rearward fan noise, and the total engine, etc. On the approach, you will see that the airframe is probably more dominant than the engine lately, and that airframe contributions come from slats, flaps, landing gear, and airframe. So that's basically what these plots show. And as you go for this lower fan pressure ratio, we see that the fan exhaust fan inlet, jet, combustor noise, LPT. That's the kind of a ranking we see. And due to the dominance of the fan noise, we need to focus on fan source noise reduction and nacelle technologies, including installation. So as you go for this higher bypass ratio, in order to reduce the diameter, we're going after this so-called slimline nacelles, where the nacelles are becoming very thin. So that means to get the weight and drag down. So when you do that, the amount of real estate that's there for the treatment becomes small. So you need to have very innovative liners that will meet this noise reduction. And a concept was shown, I think Collins, about trying to, how do you include lip liners and still meet the de-icing. And same thing, you need to come up with innovative liners to put into the liners in the thrust reverser, where the envelope is also very thin. So higher bypass ratio engines also, we talked about how closely they need to be integrated with high lift devices to minimize the installation penalties. And last but not least, the airframe architecture, including high aspect ratio wing design, may provide significant benefit because of low speed performance improvement that reduces required thrust. So such designs will also reduce landing speed, which provides airframe noise reduction. So as engine source levels go down, landing gear, high lift devices contribution at approach becomes more important. So we talked about how do we get these slats and flaps landing gear reductions down. Clean 3, Boeing has some very innovative ideas that we'll explore. So Eric Nesbitt, Boeing used to say this called stumps in the swamp. As we drain the swamp, it means as you reduce the other noise components, suddenly what were there become more evident and we need to go after them. So in that sense, the LPT and the core noise, we can't ignore them. So we need to keep all this, it's like a whack-a-mole. You need to keep, hitting all these noise sources with creative solutions. Okay. Next chart, please. So we talked about the first 3 bullets. I will now talk about some of the NASA FAA partnership, how we are approaching these challenges. Yeah. Next slide. So this is kind of a busy chart, but it shows how the NASA FAA tech maturation for sustainability has been consistent and complementary. NASA typically has focused on the low to mid TRL, and FAA is typically focused on the mid TRL. So you see the NASA's swim lanes, a lot of concept technology studies on the subsonics, in electrified aircraft propulsion, transonic thrust-based wing, etc. They have been going on for a few years, and they have advanced in the state of TRL on those things, including composites and so on. So as these technologies keep maturing, and as the FAA's clean programs also start delivering new technologies, these things we think are bringing us to a point where some of these technologies need to take to the next leap, next step in terms of some kind of a flight demonstration. That's what we call a Sustainable Flight National Partnership, SFNP. Clean 1, 2 have also fed near-term environmental technology implementations. And you may say, what are those? Some of them are like TAPS combustors and adaptive trailing edge wings, nacelle liners, etc. So it has served both the near-term implementation as well as a longer range implementation for a new flight demonstration activities. So NASA and FAA members routinely discuss their programs and learn from each other. And NASA has been developing something known as a Fab 4 technologies. We'll talk about that in the next chart. That's one of the key elements that to be considered for the SFNP. Next chart, please. So once we think that we are developing these technologies, which is the opportunity that we should invest in? So this one kind of talks about how to identify such an opportunity. Like we said, NASA FAA have been developing these innovative technologies for more than 10 years and worked with the US industry and academia to accelerate those technology maturations through a range of research and development programs. And based on this investment, we think we can target 25 to 30% lower greenhouse gas emissions compared to the best in class, for example, the MAX or the A320neo. And we want these technologies to be scalable, meaning we want them to be able to go from single aisle to a wide body and maybe even go to the regional side. And such technologies also need to bring in commensurate reductions in noise and emissions that impact local air quality. So in that sense, we think we are at a point where we need to jump to the next step of tech maturation through a flight demonstration. But before we go there, let's take a look at the three circles, the three pie charts on the right side. The top one shows the global market value. Second one shows the CO2 emissions from global commercial operators. And third one shows the population exposed to significant noise within the US, 65 DNL. By seat classes, the orange color on these are the single aisle, like a 737 MAX. The gray is the contribution from the wide bodies, like the 787s, 777s, A350s, etc. The blue sliver is the regional jets, and then the orange or the yellow one is the freighters. So what you see is between the single aisle and the wide body, they pretty much contribute to the 85 to 95% of the market value or CO2 emissions or the noise. So it makes sense for us to focus on those. And then you may say, we think a single aisle is probably the right one to focus on because lately the wide bodies have been recently introduced. The 777X is in the process of getting certified. A350 is on board. 87 is on board. So probably the next vehicle of interest will be the single aisle. So that's why we think a single aisle, clean sheet single aisle airplane is probably the right place to focus this on. And it contributes 55% of the global market value, 40% of CO2 emissions, and 61% of noise pollution within the US. So that's where we think we want to go through for a flight demonstration. Okay, next chart, please. This one is a little complicated chart, but what you show is the timeline. The red line shows the non-US industry activities. You'll see that, and the blue line shows what the NASA, FAA, US industry have done so far in terms of technology development. And based on public knowledge, we know that the COMAX C919, United Aircraft Companies MC21, and A321XLR, these are all the airplanes that are about to be certified, probably will be certified in the next couple of years. And we expect Airbus to continue to improve the A320 family through this decade and consider maybe a replacement for the A320 in the early 2030s or mid 2030s. And meanwhile, the NASA, FAA, US OEMs technology development has been going on, and they're all less than TRL 6. And these technologies typically take about 5 to 7 years for product development. And we think these technologies can deliver 25 to 30% lower greenhouse gas emissions compared to the MAX and be 10 to 15 dBs quieter. And this one may consider stretch goals, but they're not unreasonable. And these technologies need to be flight tested to burn down the risk during product development certification. So if you look at that, and if you want to introduce a new clean sheet single aisle in the early 2030s, you need to start doing the technology development readiness. If you have to hit TRL 6 by 2028, you need to start doing some flight development, flight demonstrations in maybe during 25 to 28 time period. But such flight demonstrations are necessary to burn down the risk of some of these high risk, high payoff technologies. Okay, next chart, please. This is a NASA chart. Allow this chart. This is the Sustainable Flight National Partnership. It shows the transonic thrust-based wing. And on the bottom, you see 4 blocks. These are the so-called Fab 4 technologies of NASA. NASA has been investing time and money. One is the airplane configuration, the transonic thrust-based wing, the small core gas turbine, and then third one is electrified propulsion, and then the fourth one is the advanced composite manufacturing. We think these 4 are key elements of technology that are necessary to get an S-curve in the fuel burn reduction. The latest assessment of the transonic thrust-based wing is it provides about 8% fuel burn reduction. And it's a high aspect ratio wing. It provides like 25% increase in aircraft lift to drag, which improves cruise performance, reduces thrust requirements, reduces landing speeds. So all these attributes reduce fuel burn and noise at the same time. The small core gas turbine permits you to go to higher pressure ratio engine cycles, improves the thermal efficiency, and you can accommodate a higher bypass ratio without increasing the nacelle diameter. So you're getting both noise or fuel consumption down and the noise down. And hybrid electric reduces engine power offtakes, so engines don't have to be oversized. So the current thought is SFNP plan is being developed around the transonic thrust-based wing design. Okay, next chart, please. Yeah, this one shows a so-called integrated technology development plan. The solid lines here are the planned or on the book, so to speak, and the notional ones are the dashed lines. The SFNP is shown at the green dots there, and we're trying to target this airplane flight test, first flight test in 2026 or so. And other things you see are the other swim lanes are the Fab 4 technologies. And also we need to keep in mind there are several technologies that are being worked by the FAA and the NASA. So as these technologies develop and are ready to be incorporated, they will be incorporated into the SFNP for later flight tests. The very first flight test probably will not have all those technologies on the plane. For example, it won't have a new engine configuration. It probably will go with an existing propulsion system. But as other technologies mature, so they can be fed into the flight test programs later on. So in that sense, the SFNP becomes a flying test bed. It's an asset that can be used for not only just first flight test, for a range of flight tests in future to mature these high risk, high payoff technologies. So that's the thought process behind the SFNP. Okay, and next chart, please. So that's basically what I was trying to cover today, and some summary thoughts. So if you go to the next chart. So just to recap, aviation industry has been challenged on multiple fronts. I put a star there that goes to a recent IATA annual general body meeting presentation. It has some very interesting thoughts in that. So it reflects the concerns that we raised about some challenges and what we can do about that. We talked about the pressures in terms of climate, noise, air quality, economic impact. Necessity, the mother of invention. So when there is a problem, we need to roll up and try to see what we can do. And then, so we, by the, I said, we, by that I mean all of us, NASA, FAA, industry, academia, we need to work as one team because these are very challenging goals. And then we had to come up with innovative, creative solutions, and then look for high risk, high payoff technologies. And then we need to de-risk the technologies through the public-private partnership like we talked about. And then all the time, never compromise on safety and build on effective open communication with the public and the stakeholders. Thank you. Thank you for your attention. Appreciate that.
Thank you very much for that excellent talk. Sorry, I think I'm getting some echoes now. I'm not sure. But I wanted to remind all our watchers that you can head over to the Conference IO tool to ask any questions of our speakers all week. So head over to that Conference IO tool. The link is available on the event webpage, and then you will be able to submit any questions. I think we have a couple in there, and we certainly have some time. So Devin, I'll hand it over to you to ask some questions.
Okay. So the first one, I see based on ranking, we've been seeing in Europe that the percentage of highly annoyed have been, oh, excuse me, I didn't have my microphone on. We've been seeing in Europe that the percentage of highly annoyed have been more influenced by non-acoustic factors over the years. Even though aircraft noise has been reducing over the years, the percentage of highly annoyed has been increasing. Is the FAA planning to tackle that? Studies for traditional tube and wing aircraft are well known. A recent study from UAM have been released. Citation there.
Yes, simple answer is yes. We are looking at that, non-acoustical factors and acoustical factors. And sometimes it's just seeing an airplane bothers people rather than hearing them. And the events, number of events have been increasing every day. So it's a combination of factors that we cannot ignore non-acoustic factors in assessment of the annoyance. And all the same, we need to keep challenging ourselves in terms of how can we reduce the source noise, because that's probably the most effective way of getting the noise reduction down. Operational procedures and trajectory optimizations, etc., basically redistribute the noise. So, and if population that's helped by redistributing it elsewhere, if there's no population there, that's okay. But if not, then somebody else will complain. So you need to address multiple factors when we look at that. Mm-hmm.
So a follow-on to that, I suppose, with the introduction of ADS-B and tighter spacing, you see the image you displayed of routes in and out of Boston Logan, for instance. I think that's been a contributing factor, right, to people being annoyed under those flight paths. Is there any thought to redistributing or creating a greater number of flight paths out of those areas?
Yeah, that's certainly is a very challenging situation. But so in order to increase the efficiency, we went after those narrow range. But it's the people who are under the flight path do hear many more flights than elsewhere. And if you start dispersion, then you can reduce some of that, but then it takes away some of the efficiency gains. And also people who got used to less noise probably will get more. So it's a tough question. It's a tough challenge to how do you redistribute noise. And so the optimal solution is the source reduction. That's why you need to hit that's where the gains can be made. Okay.
Based on upvotes, do you foresee the clean sheet single aisle flight demo at a model scale or a demonstration of technologies at full scale? as an example, the eco demonstrator?
Yeah, it's a good question. Like, for example, some of the wind tunnel tests have been going on the transonic truss-based wing, for example, in terms of airframe noise and performance improvements, etc. And propulsion technologies have been going on both at subscale and engine scale. And we think we need to bring those together in terms of a higher TRL, like a 6 or so, that would require some kind of a flight demonstration on a large enough scale that the manufacturers feel that those risks are well addressed, that they can implement those in their designs, product designs. So some questions can be answered at the wind tunnel scale model. Some probably had to be done on a large scale test, flight test.
The content of aviation fuel is up to 20%. While these PAHs, some of which are toxic, are known to cause particulate emissions. What then is the plan to transition to alternate fuels, since reducing the aromatic content of the existing fuel spec would seem to be on the path? Has the FAA investigated this approach to reducing emissions and thereby contrails?
Yes.
Okay. All right. Okay, and final question here in the Q&A. Are there existing FAA and NASA programs that address contrails from aircraft, a contributor to sustainable aviation? Can you talk about these programs?
I think there are some in the Ascent COE. I would request them to go and look through the Ascent COE program. Or I can follow up with a specific question if that person is looking for something.
Okay, that's all I see here. I think we're just a few minutes ahead of break. I'll turn it back over to you, Jordan.
Apologies, on mute there for a moment. Yes, thank you very much, Mooney, again for that wonderful talk. And yes, we have a break coming up, so we can break just a few minutes early. We'll plan to start back on time. So see you all at about 2:35 p.m., which is in just over 20 minutes. Thank you. All right, welcome back, everyone. I hope you had a good quick break there. Just a few more presentations here to get us to the end of the day. We do have a slight change on the schedule. Matthias will be, the presentation that was scheduled for him will be presented instead by Davey Bruza. We look forward to hearing some of his work on engine modeling and core noise. Quick reminder before he begins to, again, head over to that Conference.io tool to submit any questions that you have for the speaker or for the staff. Again, we look forward to hearing what you have to say, Davey, so take it away.
Thank you a lot for this presentation and for giving me the opportunity to present our work here at Stanford on the engine core noise study. So I'm presenting on behalf of Matthias Ime, and I'd like to acknowledge as well Changchao Xiao, that was a postdoctoral researcher here at Stanford and did a lot of the work that I'm presenting today. I also like to acknowledge funding from AARC, as well as NASA for being partners in the different projects we've been working on. So also with some motivation on the analysis and the modeling of engine core noise. So reduction of noise from jet engines was achieved mostly through increasing the bypass ratio, which lowered the exhaust jet velocity and associated noise. As a result, engine core noise has become a non-negligible contributor to the overall sound emitted, especially at lower power engine conditions. So it became necessary to optimize all noise contributors to meet NASA's future technology goals. And in addition, the introduction of advanced combustion strategies, such as lean pre-vaporized premixed combustion or lean direct injection, can result in increased noise emissions, due potentially to the occurrence of thermoacoustic instabilities, thermal stratification, and higher turbulence levels. Other factors, such as the consideration of higher overall pressure ratios and the introduction of engine designed with higher power densities, can also lead to the increase in the overall noise emissions. So I'm going now a bit more into details of what is engine core noise. And it has several contributors when we're talking about engine noise. Ranges from the inlet, where we have the fan and the compressor, all the way down to the jet noise. And when we're talking about engine core noise, we're really talking about the noise that wouldn't be present in the absence of combustion processes. And this can be divided in two subcategories. First, there is direct combustion noise, which arises from the unsteady release rate occurring in turbulent combustion, and which create acoustic waves through compression, expansion, thermal effects. But there's also indirect noise, which arises from the acceleration of inhomogeneities created by the turbulent combustion when these interact with the downstream turbine or nozzle. And there are three types of inhomogeneities that can produce noise in this way. We have first entropy noise, which is created when we have temperature hotspots that interact with the downstream components. Second is vorticity, which has been mostly studied in the context of interaction with turbine blades. And finally, the third one, which was only shown recently to be able to produce sound, is compositional inhomogeneities, meaning inhomogeneities in species concentrations. So this last component has been barely studied, especially in the context of realistic gas turbines. So one of the goals of this study is to identify the contribution of compositional noise and, more generally speaking, the relative contribution of the different sources that we discussed, and that in the context of a realistic gas turbine combustor. There is also vivid interest to develop reduced order modeling approaches for the prediction of engine core noise, and identify what kind of assumption can be made when using these models is of interest. So specifically here, we are assessing the effect of the model shape of the inhomogeneities on the noise emissions. The third goal is to assess the effect of changing operating conditions on the noise generated. To do so, we use the hybrid modeling approach, which combines LES for simulating the combustor with a linear Euler model for the noise transmission and generation of indirect noise through the nozzle. And for this, we consider realistic RQL gas turbine combustor. So this is the experimental configuration on which we base our study, and it represents a single sector of a typical aircraft engine, which has been experimentally investigated by several groups. You can see on the bottom right a schematic of the configuration. So the air is entering through some radial swirlers at the bottom, as well as through two axial swirlers. After the primary combusting zone, there are two rows of dilution holes to quench the flame. And there's also effusion flows at the wall and also at the bulkhead part. Those were simulated in the simulation as constant flows through those boundaries. The fuel is injected, as you can see on the leftmost part of the combustor's chamber, and it's entering as a spray at a flow rate of 2.6 grams per second, which is representative of a near limb blowout condition. At this condition, the overall equivalence ratio is 0.1, and we're considering an alternative fuel with a low derived cetane number. So as I mentioned, there are two steps in this hybrid modeling approach. To be able to predict reliably the unsteady turbulent combustor, we do large eddy simulations, and those simulations also provide the inflow boundary conditions to the reduced order simulation model, which will give us the acoustic outputs. So this reduced order modeling uses linearized Euler equations, LE for short, to simulate a 2D nozzle. So we're imposing at the inlet of this simulation the acoustic, entropy, and compositional fluctuations completely independently on different simulations. And the quantity of interest is the transmitted acoustic wave downstream. So by doing several simulations, considering those different types of fluctuations, we can really identify the contribution of direct noise, entropy noise, and compositional noise independently. I will go through some more of the details later on, but first I'll focus on some of the LES results. So we're using a fully compressible solver for the LES. You can see the domain here on the right, which features an upstream and downstream planet to avoid any artificial acoustic coupling. And we've been using as well some non-reflecting boundary condition to avoid any further acoustic coupling there. The mesh features 18.3 million grid points. We're relying here on the flamelet progress variable model. So in addition to the continuity, momentum, and energy equations, we're solving the transport equations for mixed refraction and progress variable. And we're also using a thickening flame subgrid scale model. For the spray itself, we're injecting the droplets with a Rosin-Ramler droplet diameter distribution. And we're using a Lagrangian spray droplet model with a secondary breakup model. I'm not presenting here for lack of time, but we did a validation of this simulation against experimental data for the flow field compared to PIV results, as well as comparing the spray velocity, droplet diameters, as well as some OH chemiluminescence data. So I'm showing here some statistical and instantaneous results. The instantaneous ones are on top, statistically average at the bottom panels, just to give a sense of what the dynamics looks like in this configuration. So I'm showing the actual velocity, temperature, and mixed refraction, some of those, and you can see that there is a strong inner recirculation zone near the swirlers at the center, as well as a smaller one on the side, outer side of the flame. The high temperature region is visible and in the rich primary combusting zone, and the flame is anchored in the injector in those simulations. Animations of the turbulent temperature field can show a bit better the evolution of the inhomogeneities. So you see here the flow field, the spray, and combustion processes, as well as the acoustics, will interact in a complex way to generate direct noise. So we will have some pressure fluctuations at the outlet. You can also note that the turbulent flow field is interacting with the dilution holes pretty strongly. And this generates still some inhomogeneities behind those dilution holes, both in terms of temperature, as you can see on this one, but also on some species, for instance, here CO2 that I'm showing. So those inhomogeneities behind the dilution hole are, however, decreasing as they are convected downstream because of turbulent mixing. When you look at the exit, though, there are still some noticeable inhomogeneities in both field, temperature, and species, notably close to the wall because of the effusion flow rate, which produces some gradients in those quantities. So it will be interesting to analyze the contribution of these inhomogeneities to the generation of indirect noise. And moving on to some more details about the LE part. So there are a few assumptions here that are to be noted. First of all, is that we're using a 2D axisymmetric domain with frozen chemistry and assuming a multi-component ideal gas mixture. Diffusion is neglected in this formalism, and the mean quantities are computed from the exit nozzle in the LS, except for the velocity, which is assumed to have a linear velocity profile. I'm showing here the equations, which are solved using a central fourth-order finite difference method for the spatial derivatives and a fourth-order Runge-Kutta method for time advancement. But this is done in an in-house code, which has been validated against established benchmark cases concerning aeroacoustics. So of particular interest in these equations are the terms between parentheses in the velocity equation, which correspond to the source terms for indirect noise. So specifically, we can see the entropy term, as well as the compositional noise term, which this one is function of the mixture fraction fluctuation, Z prime, as well as the chemical potential function phi. We can look a bit more into the details of this chemical potential function, which is going to influence the strength of that noise component. So it is proportional to the change of the specific Gibbs energy relative to mixture fraction. And it can be computed through a steady Flammid solution. At this condition, we use a scalar dissipation rate of 1 per second, which resembles the combustor exit conditions in the configuration we're studying. So the chemical potential function is shown here and features an obvious dependence on the mixture composition. But it has also a dependence on the Mach number at the outlet of the nozzle when it becomes trans or supersonic due to the compressible effects on temperature, which you can see is appearing in the equation for the potential function. Another aspect which is worth noting is that for fueling conditions, and specifically the under stoichiometric, so the black line represents the stoichiometric line, the chemical potential function will be negative for those fueling conditions. This is of interest because then it means that the compositional noise will be of opposite sign compared to the entropy noise, and we'll see how this affects results later on. So the methodology to couple the LES results to the LE simulation is as follows. We first average along the spanwise direction at the combustor exit to obtain a fluctuating field dependent on the transverse coordinate y, as well as time. And because of the acoustic response of the nozzle is frequency dependent, it is interesting to consider the fluctuations at different frequencies. And to do so, we use a model decomposition, which is basically here FFT. So from there, we consider two methods. The first one assumes a planar inlet, meaning a uniform flow field across the combustor exit. And the second method considers the transverse spatial profile in those inhomogeneous fields. And to do so, we apply POD to a frequency bandpass filter signal of those fields. So you can see at the bottom right these mode shapes, and notice, for instance, that for the entropy and the compositional fluctuations, they are far from planar, with higher fluctuations close to the wall. Those, as we've seen, were due from the effusion cooling. So I'm showing now some results of the pressure field in the nozzle due to the direct noise on the left, entropy noise at the center, and compositional noise on the right. So we also tested the Gaussian shape profile, but I won't get into this here. It is obvious, though, that the inlet profile does influence on the nozzle results. And maybe of more interest here than really the shape of those fields is what is the acoustic output there. And to do so, I'm showing that table here, which is showing the contribution of those different sources, direct noise for acoustics, entropic and compositional noise, as well as the total emitted sound. What you can see is that there is a prediction of the total noise, which is increased by 6 to 7 decibel when we're considering the POD mode. So that basically when we're using this hybrid methodology, which couples LES to the LE, the planar mode assumption is probably too reductive, and spatial inhomogeneities should be considered. We learn as well some interesting things about the relative contribution of the different sources, which are shown here in these graphs at different outlet Mach numbers. So first of all, there seems to be a negligible effect of the Mach number for each noise sources, at least for the range considered here from 1 to 1.5. But we also found that the entropy and compositional noise were dominant at the lowest frequency considered, which is here around 200 Hertz. Interestingly, though, they cancel each other out, as mentioned before, because of the negative chemical potential function at the conditions that we considered here. So it shows that the consideration of compositional noise is crucial to predict the overall noise, as in this case, it will cancel the entropy one. And we can see as well that at higher frequencies, both entropy and compositional noise will become negligible and direct noise dominates. So in the second step, what we did was extending those simulations to study the effect of operating conditions on the noise emitted. And we simulated two different conditions. The first one is the cruise one, which resembled the condition that I presented before in terms of pressure, operating pressure in the combustor, but at a higher mass flow rate, which leads to a thrust around 20 to 30% of the maximum power. And we also considered a takeoff condition, which arguably would be more critical given the noise repercussion it can have on the people on the ground. And it operates at a higher combustor pressure and even higher fuel flow rate necessary to reach the maximum power output. I'm showing here some snapshots of the temperature field with those two conditions, top being cruise and bottom takeoff. And the experimental measurements that we had at cruise condition showed that the pressure fluctuations inside the chamber drastically increased when we increased the flow rate to that level. And as previously, we also did retrieve this increased oscillation and actually a thermoacoustic instability at the cruise condition for the simulations, as well as also an instability at takeoff condition, for which we didn't have any experimental data. So even so, the combustion is still mostly confined in the primary zone, but some strong hotspots were periodically convected across the dilution holes, as you can see in panels C and D, for instance. These fluctuations, both in temperature and species compositions, were higher at takeoff condition. So I'm showing here, by doing the same methodology that we applied on the previous case, computed some pressure level at different frequencies for the different noise contributors. And these results showed that the total peak sound pressure level is higher by a few decibel at takeoff condition. At higher frequencies, though, the SPL predicted for the takeoff condition is up to 20 decibel higher compared to the cruise condition, both for direct and indirect noise. So similarly to the we previously discussed, the entropy and compositional noise exceeds the direct contribution at frequencies below 1000 Hertz, roughly. However, the main difference is that the contribution from compositional noise is 10 decibel higher than entropy noise, and that for both cruise and takeoff condition. This implies that compositional noise is the dominant source. And we can explain this by the higher fuel flow rate and the presence of the thermoacoustic instability, which led to higher species fluctuations at the combustor exit. Compositional noise and entropy noise are still of opposite sign though, but not of the same amplitude, and that explains why they don't cancel each other out. So in this talk, I presented a hybrid methodology that combines LES for simulating the combustors to a LE approach for predicting the direct noise transmission and the indirect noise generation across the exit nozzle. We found that compositional noise is of opposite sign compared to entropy noise at fueling conditions. And indirect noise has an appreciable contribution to the overall noise emissions at low frequencies. Because of the first point, though, these had different outcomes depending on the operating condition. So if the compositional noise amplitude was similar to the entropy one, this would lead to cancellation between them and a reduction in overall noise. However, at cruise and takeoff conditions, compositional noise would be of higher amplitude and would be dominant at these lower frequencies. Either way, compositional noise is needed to predict then the overall emissions. And at higher frequencies, indirect noise was negligible and direct noise would dominate. Finally, in terms of modeling, it was found that the special mode shape at the combustor exit would significantly affect acoustic transmission and generation through the nozzle and requires consideration in accurately predicting the resulting combustion noise. So in terms of modeling, this methodology can obviously be improved, and some of the future work will consider effects of 3D fields in the LE simulations, and also maybe effects of the turbine stage on the sound transmission and the effect on the inhomogeneous field before it reaches the nozzle. Another aspect of future work, which we are particularly excited about here at Stanford, is the application of this methodology to some next generation combustor, specifically to the low emission N+3 combustor, which has been studied experimentally by RTRC and their NASA research announcement program. So the goal would be to do high fidelity simulation, which will enable us to understand better the dynamics in this combustor and to assess the contributions of direct and indirect noise at several operating conditions. The ultimate goal is to provide additional knowledge to the experimental data and assimilate both of them into a hybrid core noise model that can then be used for further development of the combustor. And I'd like to acknowledge Dwayne McCormick, Jeff Mendoza, and Aaron Riemann for their work on this topic and the opportunity to collaborate with them on this project. Thank you very much for listening to this talk.
Thank you very much, Davey. That was very interesting. I am going to get Devin on here to help read some questions. So please, everyone, turn to that Conference.io tool. The link is down below on the YouTube stream. It's down by the chat. You can get a link to that tool to input any questions.
I don't yet have any questions in the Q&A. Okay, so one of the questions, how do you plan to validate your models?
So for the LES themselves, we use experimental data, but for the noise models, it's would be of interest to have some also experimental data to validate those. That's some definitely part of future work and trying to see what kind of experimental configuration could have the nozzle. It's not an easy task, obviously, to change completely the geometry of the experimental setup to have some nozzle there. So this is a discussion that needs to be done. But I guess in the meantime, trying to complexify the model, as I said, for instance, incorporating 3D effects and trying to be as comprehensive as possible is something to be done as well.
All right. Another question here for Matthias. Is combustion hoot direct or indirect, and can your model and analysis help eliminate this source?
Sorry, what? Combustion what?
The question is combustion hoot direct or indirect? If I'm misrepresenting that.
I'm not sure what it means.
Maybe for the person that submitted that question, we can try to clarify and submit another one. Another question here: how realistic is the combustor exit condition for an actual engine? The rig probably does not have choke flow at the exit.
No, so that's why it's not really possible at the moment to compare the experimental data, which indeed does not have any choked exit. So this is what we're doing in the simulation. But as I said, we need to alter some experimental the experimental setup to be able to have a nozzle and then compare really the noise emissions through the nozzle.
David, there's a request for you to turn your camera on as you engage and answer the questions. The clarification here on combustion hoot, a howling noise associated with spool up. I don't know if this is associated with there's a well-known low frequency, the so-called orca noise associated with spool up on one of the Pratt & Whitney engines.
I see. So yes, there is some evidence in the literature, and what we're seeing here as well is that indirect noise can definitely lead to some low frequency response. So I believe it has been shown that it is possible for low frequency instabilities to be due to the background effect of indirect noise. I'm not so sure about direct noise. It definitely can lead to some instability. I'm not sure exactly about what would be the frequency range of those instabilities.
Okay, and given that context, then the question is, can your model and analysis help eliminate this source?
So if we're talking about how that noise can lead to thermoacoustic instabilities, then it needs to be coupled back. So in the simulations we've conducted, it's only a one-way coupling between the combustor and the noise that is emitted outside. There will need to be a backward coupling that is also of interest for future work. If so, then yes, it's definitely possible then to analyze the fuel operating conditions and maybe develop some lower-order models to try to get rid of those instabilities. I guess that would be one of the long-lasting goal of these kind of studies.
I know your analysis is done in steady conditions as opposed to transients, i.e. the condition during spool up.
Yeah.
Okay. So we got a couple more here. Can you restate what you mean by low and high frequencies for combustor noise? Slide 18. Typical combustion noise model suggests peaks in the 300 to 600 hertz range, and suggests that it is the direct noise component, as indirect has traditionally been a very small contributor. Just trying to reconcile the frequency statements with traditional results.
Sure. So here, the low frequencies were around 200 hertz, which, again, I wouldn't make any conclusion on their role on the thermoacoustic instabilities, as we didn't take into account that backward coupling. But those were what we call low frequencies, around 200 hertz. And indirect noise was dominating even up to 1,000 hertz, and then direct noise was the major contributor.
Okay, so relatively speaking, low and high frequencies.
Yeah, that's what I meant by those.
Okay. One more question. I think it's time now. Jordan, do we have time for one more? Or we
can finish up that last question quickly and move on to the next.
As you may not know the combustor exit impedance value, could you parametrically evaluate for a range of impedance values?
Oh, so I guess the point is the impedance towards the outlet, right? Like the field. Yes. Also, so it's possible to, yes, definitely have different impedance values. It's also possible to just simulate with our LE code the outlet, the far field, basically. So that's also a possibility. In that case, we wouldn't need to do any assumptions about the impedance.
Okay, that's all we have. Thank you.
Yep. Thank you very much, Davey. We will move on to our next speaker, which is Brian Howerton. We'll be discussing some liner technology research that's been performed at NASA. So without further ado, Brian, take it away. Thank you.
All right, thanks. Switch this here. Hopefully everyone can see this. Can I get some clarification?
Yes, we can. Sorry.
Everybody good? Okay. Good afternoon, everyone. I'm Brian Howerton from Langley, and I'll be presenting some recent experimental work on acoustic liners by the Langley Liner Physics team. For those of you who are not familiar with our group, and as the name implies, we work to understand the physics of liners in order to develop acoustic treatments to reduce aircraft noise and the drag associated with those treatments. The goal is not only to come up with and experimentally evaluate liner designs and concepts like those shown here, but to also develop the tools and methods for modeling and simulation so we can understand the benefits of liner use in various applications. Our productivity has been greatly enhanced by the rise of additive manufacturing and advanced robotics employed by us and our partners. These tools have made fabrication of the necessary test articles much more efficient and less costly than even a decade ago, allowing us to explore more ideas than ever before. The work detailed in the following slides was done by the folks shown here, comprising a mix of civil servants and contractors, with Mike Jones as the lead. We also connect with our counterparts at Glenn for certain projects. The experimental equipment for the team is housed in the liner technology facility that has been operating for over a decade now. The 4 major rigs are numbered in the photo and allow us to determine the acoustic impedance characteristics of a liner under various conditions. We run on average about 20 tests a year, split between internal research, collaborative work with other centers and universities, and testing for industry. The industry testing is usually done under reimbursable Space Act agreements and has recently averaged about $200K a year and has seen significant growth in the past decade. Our rigs work at relatively low TRLs, which have the advantages of being cheap to build samples for and operate. But that lower TRL hasn't put off our industry partners, though, which consider the LTF a critical facility for their noise reduction efforts. The first part of this talk is going to focus on what I term fundamental research, where we're looking to understand some aspect or component of liners and how that aspect affects overall acoustic performance. The next few slides will focus on efforts to improve the lower order models we rely on to do liner design optimization. These models may lack the fidelity of something like a full-up COMSOL simulation, but they are quick and can be accurate enough for initial designs where we may need to sift through thousands of variations and search for the most promising. We're going to show some experiments done in the NIT from this building block approach for some liner components. What's the payoff for all this? We want to use these models to rapidly evaluate full engine what-if scenarios using our liner concepts and the computational tools for source modeling and propagation developed by the group. The first study we're doing is focused on figuring out the best phase sheet perforate impedance model to use. In phase 1, we're testing a large number of phase sheets in the normal incidence tube at Mach 0 over a common core with variations in porosity, hole size, and material for multiple acoustic sources and levels. The two microphone method is used to determine the experimental acoustic impedance, which is compared to predictions from 15 models culled from literature to see how well they match. So far, Motzinger and Kraft's model compares best to the experimental results, but that may change as we test and analyze more configurations. And I also want to give recognition to Acoustics for manufacturing the carbon fiber face sheets under a Space Act agreement we have with them. We're also looking at the effect of cell partition thickness on educed impedance for straight chambered liner cores. On the lower left, you can see the cores tested in the NIT using a common conventional perforate face sheet. The plots on the right show the measured impedance spectra for each thickness as solid lines with the corresponding predictions as dashed lines. The comparison between the two is very good as long as you account for the change in surface porosity as the partitions get thicker. Noteworthy is a general flattening of the reactant spectra with increasing thickness, which can be favorable for absorption. We're also working with Honora to investigate the effects of partition thickness on interactions between adjacent chambers. Some of our liner concepts take advantage of bent chamber cores to efficiently package the longer chambers necessary for low frequency absorption without resorting to excessively thick liners. Much of our initial research with bent chambers employed 3D printed configurations with relatively thick partitions between chamber segments. These can be predicted well as long as you account for the surface porosity as mentioned before and include the Cummings correction for the bends. Working with our partners at Hexcel under a Space Act agreement, we put together some thin wall core samples from fairly standard phenolic honeycomb, but removed selected portions of the partitions between adjacent chambers at the bottom of the core to create a bent chamber. So think of them like strategically placed drainage slots. The plot on the right shows some impedance results for configurations with and without the slots. It's interesting to note how little effect the slots have until you get to the higher frequencies, but we still get the benefit of the longer bent chamber. Now we want to look at the effect of partition thickness for variable depth liners. Matt Gallus is working through a test plan now to evaluate a large number of core and face sheet combinations. The cores are designed to target various frequencies with and without harmonics, and will be tested uncovered with no face sheet, as well as with a linear wire mesh and two perforates to get some nonlinear effects. The plots on the right are impedance spectra from some recent measurements with two cores, both uniform and variable depth, and a couple of face sheets to give you an example of what we're seeing. Analysis will include comparison to predictions using transmission line codes, and a down select to a few combinations that will be built and tested in the grazing flow impedance tube so we can incorporate flow effects. So stay tuned to find out what we learn on this. Now, most conventional liners are weakly nonlinear with SPL, so local impedance should vary somewhat along the length as the sound is attenuated. Right now, when we induce a liner's impedance, we assume it to be uniform over its axial extent, even though we know that probably isn't the most accurate answer. So we're now looking to investigate this in detail to see when and how much this SPL effect matters. The topic brings up two fundamental questions. Do we see a bigger effect near the resonant frequencies when the liner should be doing a good job attenuating the incoming sound? And what happens when we introduce grazing flow? Are we going to see any variation diminish when the Mach number is increased? The acoustic data for this has already been acquired in the GFIT using samples with a common core and face sheet design, but varying the liner length to get an axial SPL reduction. We've taken this idea and run it through our iterative convected Helmholtz equation-based deduction code, usually referred to as the cheat code, in two ways. First, the impedance was assumed to be uniform, as we've always done, and we get an answer that way. Then we divided the sample into three axial zones and allowed the code to solve for the impedance of each simultaneously. This zonal approach takes significantly more time to compute as an answer due to the additional degrees of freedom the optimizer has to deal with. So it would be good to use this approach only when necessary. We're still looking at the data, but the initial results confirm an effect near resonance, especially when the grazing flow Mach number is low. As part of our collaboration with Honora via an international agreement, they are exploring the use of continuously variable impedance models to evaluate this data. As part of our continued participation with the International Forum for Aviation Research, we've put together a new challenge looking at source effects on the induced impedance of a liner. The plan is to take 4 liners, 2 of our calibration liners that we've tested previously, and 2 conventional ones used in previous IFAR challenges, and test them with a variety of source conditions. We'll analyze the data with our methods and provide the measurements to the partners so they can apply their tools and compare the impedance results. The intent is to help the partners gain better understanding of each other's processes and how to interpret their products. Testing is underway and should be complete by the next technical working group. So now that I've talked about our fundamental research to understand more about the components of liners, I want to show some of the full-up liner concepts we've been evaluating along with some selected results. One such concept is what we term the active liner, developed in conjunction with Boeing and Florida State University under an NRA. The idea behind it is to use a controlled variable porosity phase sheet to alter the liner's impedance spectrum. The lower left image shows the implementation, which is accomplished by stacking 3 perforate sheets with match drilled holes and sliding the middle sheet relative to the other 2 using an SMA wire. The video in the middle, taken with a microscope, shows the actuation to various perforate openings. We've tested this at the GFIT at Mach 0.3 with sound to determine the liner's impedance characteristics as shown in the upper right figures. One can see that we get some noticeable changes in both the resistance and reactance as the openings are adjusted. We also took some drag measurements with no sound as shown in the lower right. It was surprising a bit to see that we didn't get a lot of variation in resistance factor as the porosity was varied. But this could have something to do with the stacked face sheet construction, which is a bit atypical relative to conventional liners. Tests are ongoing for no flow and at higher Mach numbers, so look for further results in the coming months. Chelsea Dodge, in addition to her work on the active liner, has been looking at the deal concept, whereby a dielectric elastomer embedded septum is placed in the core, similar to a 2 degree of freedom liner. The figure on the left is an exploded view of the components with the elastomer in the middle. By altering the compliance of the elastomer through the application of voltage, you can change the liner impedance characteristics. Right now, she's doing laser vibrometer tests to measure the displacement of a sample piece of elastomer when subjected to acoustic excitation from the backside to characterize elastomer response. The plot on the right compares the measured displacement of the membrane to theory and shows good agreement until you get to higher sound pressure levels where things get nonlinear. The purpose of this data is to validate the elastomer response model she's developed for use in optimizing the next version of DEAL. Martha Brown has continued her work on the variable phase sheet concept reported on previously, where she's looking to alter a liner's impedance characteristics by locally varying the phase sheet geometry. What we've seen is that you can take a simple uniform depth SDOF core and by changing hole size, porosity, and hole distribution, get a much more interesting impedance spectra as shown in the lower left figure. The black lines are for a uniform phase sheet and core and give a spectra like one would expect. Applying the variable phase sheet shown to the same core results in a much different spectrum. The nice thing about this effect is that we can do a pretty good job at predicting it even with flow. The right plots show a case at Mach 0.3 of measured data from the GFIT, the solid lines, versus the dashed lines, which are SPL predictions using a Prony-derived impedance and the convected Helmholtz equation for propagation. You can see that the agreement looks pretty good. So based on this, we want to employ an optimizer to explore the design space and determine how effectively we can alter impedance. These next few slides are going to focus on improvements to the testing techniques employed in the liner technology facility. So far, we've been working in the area of liner drag for a while now, having implemented a way of measuring relative drag between liners via determination of their resistance factors shown by the expression in the middle of the slide. With it, studies have been done to report the effects of phase sheet porosity, frequency and SPL variation, perforate hole size, and perforate shape on drag. This led to tests of perforate shapes that weren't the round hole typically used in an effort to reduce the liner drag penalty between treated and untreated surfaces. Our best design uses slots with the long axis perpendicular to the flow and cut the penalty by 50%. We've tested other slot-derived designs, but statistically, we're unable to discern any differences in the configurations due to measurement uncertainty. Recent work has shown that by operating the G-fit at a constant static temperature and dynamic pressure, we can reduce day-to-day uncertainty by a factor of 6 compared to using constant Mach number. We plan to redo the 2018 study to see if any of those perforate configurations yield additional drag reduction, and look to see if previous data can be normalized via these parameters. These results will be published in an upcoming AIAA paper. Over the past few years, we've been slowly gathering the resources to replace the CDTR microphone array, which was experiencing some environmental degradation that couldn't be repaired due to the design of its electret-based microphones. The new array uses condenser microphones of the same type we have in the G-fit and shouldn't have those issues. An additional benefit of these new mics is the ability to implement a much simplified calibration method based on the approach we use in G-fit. Rather than requiring a laborious multi-frequency calibration done one mic at a time, we can calibrate the entire array simultaneously in place with single frequency excitation. The process starts by putting in a hardwall liner, then turning on the drivers at 350 Hertz to generate a plane wave. We then use a pair of microphones from the downstream array to acquire measurements with the two microphone method to determine the duct exit impedance. The exit impedance gives us a way to compute the standing wave pattern in the duct, which provides the theoretical correct SPL and phase for each microphone location. Take data with the full array, then compare the measured results to the theory to get the necessary corrections for each microphone. There is some bookkeeping involved behind the scenes, but we can now do in 5 minutes what used to take us at least 2 days, and that's a big time savings. So since the last technical working group, we've also done some work with Dr. Hovard Vold under contract to extend the swept sign method of data acquisition and processing to handle the grazing flow environment of the G-fit. Swept sign has been our preferred method in the NIT for a few years now because of the efficiency it offers without sacrificing accuracy. To deal with the flow noise present in the G-fit, some adjustments were necessary to improve spectral estimates and account for the microphone array layout. The plots on the right are impedance spectra from one of our calibration liners at 120 dB, acquired with the traditional step sign approach, the dots, compared with the corresponding swept results for two Mach numbers. The swept results are shown in lines. The agreement is good, especially away from the anti-resonance condition near 2 kHz. But not shown here is that agreement gets even better at higher SPLs with their increased signal-to-noise ratios. So we feel comfortable using this method for grazing flow in the G-fit. So now that you've seen all of this experimental work, here's a freebie from the computational side. Through a Space Act agreement with Boeing, NASA has been given the realistic nacelle and flow path geometry for 3 classes of turbofan engines. Think small, medium, and large. We're pretty excited by this as we've never had such information before, with reason being that now we can use all the tools we've developed for liner optimization to apply our concepts in various configurations and assess the acoustic benefits. We also get to understand more about the locations and volumes available within the engine where treatments can be applied. Going forward, it would be good to include metrics for things like cost and weight to understand how that feeds into the producibility of a configuration. We also expect this engine data to help with our efforts in developing a new liner module for the ANOP systems analysis tool, and assist with understanding the interactions between various noise control technologies when applied throughout the engine, so we can accurately determine the overall system benefits. So now, a while back, we were contacted by the U.S. Department of Agriculture's National Peanut Research Laboratory regarding methods to reduce the noise generated by crop dryers used throughout the industry. Now, these dryers have a lot of similarities to the engines we usually work on, with their multi-bladed fans and propane burners enclosed in a duct to blow heated air into trailers full of harvested peanuts and such. You can see examples of these in the photos below, and here's what one sounds like in operation.
Brian, we're not getting that audio through.
Well, let's get you that audio. How about it? We got a minute.
Did you select the when you broadcast, when you click share screen, there is a include computer audio toggle switch that you need to flip to share the audio.
Yes, I do remember that now. So let's do that. Let's stop and then restart, and then include computer sound, and go back to you, and then return to the slideshow. Now let's try that again. So now imagine a dozen or more of these running simultaneously in close proximity to each other, as is the case at the distribution centers where crops are brought for sale. These centers can be near populated areas and cause annoyance to the community. From the recording, one can hear the combination of tones and broadband as shown in the upper plot of the noise spectrum. So this led us to suggest some sort of bulk absorber as a first cut at a liner. The photo in the lower right shows a test muffler with a high porosity perforated inner wall and a rather deep annular cavity to be filled with the bulk material. One suggestion we had was to pack it with used peanut hulls, since they should be readily available. The plan is to test this on a dryer and make a fair number of noise measurements to get directivity and distance effects. And based on those results, we could offer them some ideas for improvements. Certainly this is outside our normal liner applications, but it's an interesting problem. So now we want to offer folks an opportunity to collaborate with us on a comparison study. And to give you some background, back in the early 2000s, NASA and some of our industry folks did one of these collaborations where we tested similar liners in each organization's rigs and compared impedance spectra educed using each other's methods. And these were fairly simple SDOF configurations in our flow impedance rigs. And we want to try to revisit some of that and look to do a newer study, but in a similar vein. Since that was done many years ago, we've got better tools, better rigs, and now with this aforementioned developments in additive manufacturing and some of the novel liner configurations that have come about, we feel like it's time to maybe do one of these again. So the collaboration has two areas of interest. One is an experimental focus, looking at our data acquisition tools, similar to what we did before. But we also want to add a computational focus to look at the impedance eduction analysis. And what we propose is the idea of us giving the partners design info for a few liners, some of them like our calibration liner or regular SDOF perforated over honeycomb type stuff. Each of the partners builds those liner configurations to fit in their specific test rigs, and then we do some testing. And we share data back and forth in order to see how that works out with each one, and for the various liner configurations that we've put together. Now on the computational side, NASA's going to test some liners in our facility in the GFIT and provide the acoustic pressure data and associated flow measurements for those. And then each of the partners will process that data using their eduction methods in order for us to compare back and forth to see where the differences are. And then we'll do a data exchange again to try to understand what each group brings to the table, and where we might be able to improve our methods. With that, I'll be happy to take any questions that you may have, and thanks for listening.
Thank you very much, Brian. Again, I'll invite Devin. It looks like we've got at least one question, so everyone please head on over if you have any questions for Brian to that Conference IO tool.
All right. How is damping represented in the simulations? Is it mainly radiation damping across the outflow boundary conditions, or are there internal absorption mechanisms?
Well, I am going to have to defer that question to, if I'm understanding it correctly, I'm going to have to defer that one to one of my colleagues, because it would be good to know which slide he might be referring to in terms of or the person might be referring to in terms of this question. Because there's, we do simulations with transmission line codes, with COMSOL, with a fair number of codes. So it would be good to know which one in particular they might be referring to.
Okay, if the contributor can submit another question to that effect. I see a pretty early timestamp, 2:07
yeah, it was
my time. So
I saw when it came in, and it had to do with one of the early slides. Just curious as to which one they might be talking about.
So with your curved internal channels, or rather deeper internal channels that are I guess curved isn't the right word, but
about these.
Yeah, the 3D printed ones. I was actually going to ask if curving the smoothing the corners could offer any improvement, or if it's worth anything.
The idea that you're not having an area change, I do think would help, but it's not as convenient in terms of fabrication and packaging to potentially curve them as opposed to the square it off. But yeah, I mean, we could still predict what's going on with them, even square it off. So it's I mean, we have seen others do it in a curved sense, and actually we've done some configurations that have ended up into some applications where it ended up being that way, and it's there's no reason why you couldn't do it that way.
And now regarding the variable lengths of your test samples, 12, 16, and 20 inches, are those all just within the confines of your the GFIT's capability? How expandable is it?
The GFIT can handle up to 24-inch long samples, and we had a 24-inch long sample, but it broke. It got so we haven't printed another one yet, and but we feel like we can get the answers that we need out of these three that we have in hand.
Now, just curious, for the sake of yeah, there have been many studies on manufacturing tolerances with additive manufacturing. Do you have a preferred method of additive manufacturing?
It's been our experience. Most of the samples that we have had built have generally been done using stereolithography, and there it's a question of the resin that you want to choose. Some are more dimensionally stable than others, but oh yes, we have seen variation in creep at times with moisture absorption and such, and so we do take some care when we get those kinds of samples in to package them and store them so that try to mitigate those effects as much as we can. And we're also starting to look at different resins. They're getting better all the time, and it's just a matter of taking the time to go try some new ones and make sure that you're not trading one problem for another.
Mm-hmm.
But yeah, whenever we get something that we printed in, we go through a quality assurance process to make sure that we understand what we got versus what we asked for. And some of the companies have gotten better about altering the build parameters so that they compensate for shrinkage and such.
Well, thank you very much again, Brian. It looks like we've come to our time. So
okay, and so we've captured that question. I don't see any more on that Q&A. So if that person, the Q&A remains open. So if you want to, again, referring back to this slide set, clarify the question, it can be answered later.
Great, thanks.
Yes, thank you for that, Devin. And thank you, Brian. We'll now be moving on to David Lockhart, who will be discussing some airframe noise research again from NASA. So again, David, take it away. Thank you.
All right, thanks. And let me just go ahead and share my screen. That's interesting. All right, there we go. So yeah, I'm going to give you an update on some airframe noise research. And for those of you who've been at the previous TWGs, probably no surprise that I'm going to talk a little bit about the high lift variant of the common research model. We completed a test of that in April of this year. So we have continued to do some processing of that experimental data and use some unsteady numerical simulations to help understand some of those results. And that's what I'm going to present to you today. So if you weren't here for any of the previous TWGs and you need that background material, you can get that by looking at ntrs.nasa.gov. So I showed you results for our slat gap filler. So this is a picture of it over here. We used a shape memory alloy, had these smooth conformal tips. And comparing with the baseline, that's in black, our 1/12 octave SPL as a function of the model scale frequency. When we used the standard cutoff tips, we got the result in red. With the conformal tips, then we got this result in green and pink. So, upwards of 10 dB of noise reduction. So I showed that the last time. But what I didn't show you is the noise reduction at all the different directivity angles. So we had this microphone array that could traverse on this little train. I did show you some directivity results, but not for the SGF. But you can see as we go all the way from full upstream at 56 degrees to downstream at 120, we get good noise reduction across that entire region. For the most upstream, the most upstream result, which is the one in orange for 56 degrees, the slat doesn't make as much noise. You don't get quite as much noise reduction at that, especially at the very low frequencies and high frequencies. But the slat noise peaks closer to 110 degrees, and that's where you get kind of the maximum noise reduction. Similarly, if you install the landing gear and look at the directivity again at all the angles, you're still seeing about 5 dB in noise reduction, a little bit less again at the most forward angle, the orange, because first of all, it's not making as much, the slide isn't making as much noise, but also now you've installed the landing gear, which is making a fair bit of noise. But after doing the full processing, we're now pretty confident that across the directivity, the slat gap filler is giving us good noise reduction. I also showed you this result where we looked at the effect of the slat cove filler and the rather disappointing noise reduction that we got from it. So in black, we've got the baseline. In red, the results with the slat cove filler. The very slight noise reduction we see at very low frequencies is mostly just a result of the fact that we had the gap filler on the inboard section. And we actually had a little bit of noise increase at the high frequencies. So to help us to understand this, we ran some numerical simulations, but we took the nacelle off and then put the cove filler on the outboard section, the gap filler on the inboard section. and it just looked at the noise coming from the outboard section of the slat where the cove filler was installed. And you can see at low frequencies, it matched up with the baseline without the cove filler, and a little bit of increase at higher frequencies. So it matched up with what we were seeing experimentally. So then we went and interrogated the numerical simulation to see if it could shed any light as to what's going on. And unfortunately, not really. When you look at these beamform maps for 3 different frequencies, comparing the baseline with the one with the cove filler on the bottom, you don't see a whole lot of difference, except out here at 13 kilohertz, you are starting to see a little bit additional noise coming from the case with the cove filler. But it doesn't really tell you what is causing that. When we look at the fluctuating surface pressure contours and streamlines don't really look that much different. The baseline is here on the left, and the one with the cove filler is on the right. And you do notice that sort of the light green, brownish, bluish that goes along the span in the slat cove, that actually is gone when you've got the cove filler. So the cove filler has done something to reduce some of the fluctuation levels. And the intense regions, red, that we see around each of the brackets actually is a little bit less intense around most of the brackets, although maybe a little bit more intense out at some of these outboard ones. So overall, if you just looked at this, you'd think it should be quite a bit quieter. But keep in mind, this is just the RMS. So we really need to decompose this down by frequency, because we may just be getting swamped by some very low frequency fluctuations. But overall, it really didn't help shed too much light on what's going on. One of the things that we used as a measure of goodness was the attachment of the flow on the cove filler. And you can see these streamlines show that the flow is attached, and experimentally, when we put tufts on the model, that's how it looked there too. So this is still a mystery. I'm still digging into the data to try and figure that out. Another thing I showed you previously was the effect of brackets on the spectra. So the black again is our baseline, and this is experimental result here on the left. And when we took 3 of the brackets off, brackets 7, 8, and 9 of 15, we got about a 2 dB of noise reduction by doing that. So we also ran simulations for this case. So that's what you're seeing here on the right, the simulation results. And the red again is without those 3 brackets, and we're seeing about that same 2 dB of noise reduction by doing that. But there's something else you can do with the simulations that you can't do experimentally, and that's take all the brackets off. So that's what we did. And now we see a pretty substantial noise reduction. This isn't quite as much as what we saw with the gap filler, but it's within a few dBs of that. And you see these other points that are jumping up, and it's because we're putting a box just around the slat, and there is an outboard tip source that moves around, and occasionally we'll get inside that box. We look at the beamform maps for the case without brackets 7, 8, and 9 compared with the case without any brackets. And it's pretty obvious where brackets 7, 8, and 9 are in each of these beamform maps, because that's where the gaps are in the intense noise source, and those are pretty much gone when we eliminated all the brackets. So clearly there's a very important interaction between the brackets and slat noise, at least on the CRM model. And again, if we look at the RMS levels of the pressure, when you've got those 3 brackets gone, you're missing kind of the red that you see around the brackets there. Whereas if you take them all off, they're all gone. So you're just left with kind of that greenish inside the slat cove region. Now, if you noticed, all those results that I just showed you from the simulations did not have the nacelle pylon on, and something that I've been looking at since 2018 will hopefully explain a little bit of that. So when we first started doing simulations of the CRM and did our process of this large-scale LES computation, take the solid surface data, put that into the Fox Williams Hawkins, use that to predict the noise levels at a microphone array, and then apply the beamforming technique, we almost always saw this very intense noise source ran around the nacelle pylon, which was very conspicuous. And then when we finally did an experiment and we found we did not see that intense noise source there, it confirmed that we had something that wasn't working quite right in our process. And others have been seeing this sort of discrepancy between predictions using solid surface Fox-Williams-Hawkins data. Mehdi Karami had seen it, Philippe Spilart had seen it. And they reverted to using a permeable surface Fox-Williams-Hawkins. Now, the problem there is that you now have to accurately predict the acoustic solution in your LES out to that permeable surface. And then you have to store all 5 of the primitive variables on that permeable surface, not just the pressure, which is all you need on the solid surfaces. So your computational requirements often balloon in doing that. And we simply didn't have the computational resources within this project to do that. So instead, we made the decision to just look at the full span slat without the nacelle pylon. And that's why all the results that you've seen about the CRM from me do not include the nacelle pylon when we're actually looking at the noise. But the question still remains, when are solid surface Fox-Williams-Hawkins predictions unreliable? Because I'm still using them without the nacelle pylon, and why are they inaccurate? So the rest of the talk is going to discuss one of the test cases that I've been using to try and understand this. So basically, I just have this flying rectangular box, and in this case, there is a thin inviscid plate that is beneath it. So, this is the surrogate for my intense noise source that is above the nacelle pylon. And my flat plate here is my surrogate for the nacelle. But we put all these observer points where we're going to directly sample the CFD. And then we've got 2 Fox-Williams-Hawkins surfaces, the inner one, which you see in yellow, and then the outer one, which is in red. Some of these points are inside the red one, some are outside, but for the purposes of this talk, I'm not going to go through all of them, just a few of them. So this is what the solution actually looks like. These are Mach number contours. So the mean flow Mach number is Mach 0.2, same as it was for the CRM. But you can see a very significant separated region, which is, starts right at these leading edge corners. And the wake, there's also a very low speed region. But there's also just tremendous unsteadiness inside this whole region in the vicinity of this viscous box. Parameters for the viscous box, the Reynolds number are all given here. The inviscid plate that's below it, you can see the length of this is 0.2 meters. The inviscid plate's 0.8, so it's 4 times the length. And the leading edge of it is slightly upstream of this. You'll see it in the next image, but it's placed 0.2 meters. So the length of this rectangular box is how much below the plate is. So you can see here, this is an image of the grids, and this line right here is actually showing you where the plate is. So even though it's inviscid, the calculation still picks up a little bit of effect of the plate because of stagnation occurring, even though it's really thin. But you can see how much grid has been packed in around the cylinder, and actually how fine the grid is even beyond outside the plate, out of the plate. And we need to do that to maintain the acoustics, which are going to be fed into a Fox-Williams-Hawkins surface that's outside of even this plate. And this is the very coarsest of the grids that we ended up using. So we also had to have additional refinement around the rectangular box. So you can see them. We actually end up using contours of isosurfaces of lambda 2 to help to define those. But you can see 4 levels of grid refinement that we ended up using, all the way up to 4.3 billion points, just to do some calculations around a little box. So yes, these got quite large, and the number of points per wavelength that are, the frequency for which you would have 15 points per wavelength out at that outermost Fox-Williams-Hawkins surface goes up to 18 kilohertz on that finest grid. These are the instantaneous pressure contours, and you can see with the plate here, you basically have this shadow region down here, whereas the sound being emitted by this rectangular box is able to propagate upwards without anything blocking it. So what we're really going to be looking at is the difference between what happens above and below and even upstream. So first I'm going to show you the the grid refinement for this particular case. So we picked a point that is above the box. This isn't involving any shielding or anything like that. It's where we would actually expect that whether you're using solid surface or permeable, everything should work, because traditionally this has given us pretty good results, and that's pretty much the case. The black is the directly sampled CFD. The pink here is just the plate by itself, and you wouldn't expect that to give you the right answer. You know, you should have to combine the plate plus the solid box to get anything reasonable, and indeed, if you do that, you get pretty close to the result that you get using either of the permeable solutions. As you refine the grid, the solution improves at higher frequencies, but even on this finest mesh, you know, get above 1 kilohertz, we still don't get perfect agreement. If we look then at the point that is below the plate where we've got all that shielding, now even on the finest grid, there's still a pretty significant discrepancy, even down at 3 kilohertz. And this is why I refined the grid so much. I was trying to figure out why I was still getting so much discrepancy. I think some of this is because the noise source isn't that intense. And down here where we've got all the shielding, there just isn't much solution, at least in here. But there's still some, you know, why it's different below 5 kilohertz is kind of surprising. And actually, if you look at the point that is within the red box and closer to the plate, the agreement actually gets quite a bit better. So there's some issues that I don't completely understand. But the real point is that regardless of which one of these meshes you're looking at, the conclusions are going to be the same. So I'm going to just blow up this one on the finest mesh so we can look at it more closely and determine what really is happening here. So again, the black is the directly sampled CFDs. We're assuming that this is the right answer. If I use the outer permeable surface, the one in red, okay, I get pretty close to that CFD solution. If I take the plate plus the inner permeable, so the one that is in yellow, combine those two, I pretty much get the exact same answer as the red outer one. However, if I take the solid box and add it to the plate, I then get the blue solution, which at very, very low frequencies is very close to the directly sampled CFD, then kind of flattens out and then gets to be pretty much the same as all of these other solutions, which are the permeable inner by itself and the solid plate by itself. In fact, the permeable inner and the solid plate are almost identical. They lay on top of each other, except at the very lowest frequencies. So, you know, I'm doing these various combinations, and you know, one of them gives me the cancellation that I need, and that's the one with the plate and the permeable inner, as opposed to adding the plate to the solid box. And it, you know, the solid box is the orange one that's up here. It's actually all three, the solid box, the solid plate, and the permeable inner are all pretty close in terms of this absolute amplitude. And yet only the combination of the solid plate with the inner permeable give you the kind of cancellation that you need in order to get that saddle region correct. So ultimately, the phase must be very different between these different solutions. And if you actually do plot the phase, that is what you see. So I think this is telling us that, you know, we're getting a lot of phase issues caused by propagation through that very unsteady flow that we saw in the vicinity of the box. So it's not just, you know, that some people speculate, oh, we got all these extra sources that are in the volume, and we have to capture those with the permeable surface. I don't think that's what's happening here. I think it's really a phase effect that's caused by that very non-uniform flow, unsteady non-uniform flow that we've got around the box. So, you know, that's what I'm continuing to look at, and it's got some other test cases that I've run to help to explore that. In terms of the CRM, there was a paper that was at the summer aviation meeting that gave an overview of the air acoustic testing results that we had from the 14 by 22 this past year. And we have 5 additional papers that we're planning for the 2022 AIAA Aeroacoustics Conference that'll be very comprehensive. And we're also hoping to use some of that CRM data in future bank workshops. Points of contact that'll be available for you in the package. And I will be happy to take any of your questions now, and also just want to acknowledge again the Advanced Air Transport Technology Project for all their support.
Thank you very much, Dave. Again, excellent to see all the hard work you folk are doing. Looks like there's at least a question, so I'll turn it over to Devin to pose it to you, I suppose.
Okay. Excuse me. Where is the permeable surface located with regards to the wing in the Fox-William-Hawkins?
I did not do any calculation with a wing and a permeable Fox-Williams-Hawkins surface. So when we were looking at these results, I only ever did solid surface Fox-Williams-Hawkins. That's doing a permeable one for the CRM. It was prohibitively expensive for my project. There have been others at NASA who have had much more resources available, computational resources available to them, and have done that, but I never did. So at least in terms of a wing, there's no permeable surface that I ever did. I was just trying to understand why is it that I had problems with the solid surface solution.
Okay, we have a couple more questions. Is that okay, Jordan?
Yeah, we're at the end of the day here, so I think you're all right to answer a few.
Okay. Which version of Power Acoustics did you use for the permeable solid Fox-William-Hawkings far field propagation, 2019 or 2020?
2021.
Okay.
2021, yeah, version 6, 2021. At least for everything that I did with the box was done with version 6, 2021. The stuff that was done with the CRM, obviously that was completed earlier, so that probably would have been version from 2019. I think 2019 R3 probably.
Okay. Did you predict the noise inside the solid or permeable surfaces to assess the spurious signals?
Yes, so if you noticed here, I had these points where one of them is outside the red box and one of them is inside the red box. Same thing below. One of the green points is inside the red, and one of them is outside. So what I showed you is the result that's outside the box. It is kind of interesting to look at the one that is inside the red permeable surface. Above it, you do see a very substantial reduction in the solution for the red permeable Fox-Williams-Hawkins. But the reduction that you see below the plate is very similar to the kind of reduction that you see up here, but that just gets you to about the level of the shadow region. So it's not nearly as low as you would think it should be. In other words, above the plate it is, but below the plate, because the levels are already so low, it's not nearly as low as, you know, this idea of the Fox-Williams-Hawkins always giving you 0 inside of the surface does not hold at that point.
Okay, we have one more question. Doesn't the Fox-Williams-Hawkins solution assume a free space Green's function? Could the interpermeable surfaces provide an accurate answer if computed using a Green's function, which accounts for the scattering plate?
Yes. So, you know, that's kind of the. There are alternatives, but, you know, sticking a you would lose the simplicity and the elegance of the solution of the Fox-Williams-Hawkins if you tried to put an exact Green's function for the geometry in there. But that may be what we ultimately need to do, is in some sense to do that. So you may be using something like the TD-fast, some other code like that can actually include the geometry in there. Otherwise, you may be subject to the kind of errors that we're seeing here whenever you've got a scattering body. So in this case, the rectangular box is physically separated from the scattering object, the plate, as you can think of, where if I took this rectangular box and stuck it on the plate itself, they're not physically separate. You still get the same sort of issue arising there. They don't have to be physically separated, but by doing it, it allowed me to play these games of adding and subtracting the different combinations to demonstrate what I did. But yes, ultimately, if we want to avoid this problem, we either deal with permeable Fox-Williams Hawking surfaces that go outside of everything, or we figure out ways to put the source into some sort of method that understands what the actual geometry is. And I'm not sure if we really need to include the details of the mean flow as well or not. I suspect not once you get the geometry in there.
Okay, that's all I have on the Q&A. Thank you,
very
David.
much. Yeah. And here, now that we've come to the end of our agenda, I want to thank all of our speakers today again for all their hard work and being willing to come here and share with you all the stuff that they're working on. Thank you as well to all the folks that helped make this possible. A lot of people at Glenn, Langley, Nari have worked very hard to pull this off. A few quick reminders. Tomorrow we begin again at the same time, 9 a.m. We will be at a different YouTube link, so make sure you head back to the event webpage and get tomorrow's link. If you come back here, you won't find us. You'll just find today over again, which if that is what you feel like watching, by all means. But if you want to see the new things tomorrow, get that new link and join us there. Unless anybody else has anything I've forgotten to say, I thank you all again, and we'll see you all tomorrow.